Okay, hello, good morning, everyone. Welcome back to the second day session of the international webinar on Rendezvous with Quantum Physics. As convener of this event, myself, Satyaki Kaur, thank you all again for joining with us today. Just like yesterday, we will try to follow a few norms here, like keeping the mics off, not interrupting the speaker in the middle of the talk, and rather keep the questions posted in the chat box, etc. Also, please note that because this is the last day, so a feedback form link will be shared in the chat box during the last half an hour of today's session. You need to fill that up to claim your certificate. Okay, so now as per today's schedule, there's lined up one keynote speech by Dr. Ananda Dasgupta, two contributory lectures by Dr. Somnath Jalal and Dr. Amit De, and two short presentations by Mr. Rajdeep Banerjee and Dr. Shampa Mondol. So without further delay, let me start today's technical session. Our first talk of the day is the one to be given by Professor Ananda Dasgupta. He's already here with us. So this is probably the talk everybody of us is waiting for most eagerly, because it starts with our beloved Sherlock Holmes and takes him right at the doorstep, or rather box step, of the Schrodinger's cat. Let me first introduce our honorable speaker, Dr. Ananda Dasgupta, to you, though most of you must have already known him. Okay, so Dr. Dasgupta is a professor from IISER, Kolkata. He did both his BSc and MSc in physics from Jadavpur University, and then his PhD from Shah Institute of Nuclear Physics in 2005. His teaching experience started as a lecturer in St. Xavier's College, Kolkata, and then as a senior lecturer in Jadavpur University. After that, he joined IISER, Kolkata in 2007 as an assistant professor, and later, right now, he's, I think, working as an associate professor there. So Dr. Dasgupta is a very popular teacher, and in social media, we often see nice video lectures of him posted for the students. We are extremely happy that Dr. Dasgupta found some time for us today to deliver his popular lecture. His today's lecture topic is Sherlock Holmes meets Schrodinger's cat. So Dr. Dasgupta, I welcome you to our webinar and request you to kindly take over the session to give your interesting lecture.
Thank you, Dr. Kaur, for this kind introduction. And I must thank the college, AKPC Mahavidyalaya, and the organizers for giving me a chance to speak here. Now, before I start, could I just get a timeline? How long do I have here for the actual?
Actually, the time is 40 minutes and then 15 minutes question answer session.
Okay. Okay. I might just go a bit above the 40 minutes. But anyway, give me a warning at 35. Okay?
Yeah.
I tend to sort of overshoot sometimes.
Yeah, okay. Means you can just go a little bit higher, no problem with that. Okay.
Okay, let me just start the presentation anyway.
Okay, thanks.
And okay, before I do that, let me just switch off my camera. There's a bandwidth issue, so maybe it's best that people don't take a look at my face anyway. So let's just switch off the camera, and then. I hope my screen is visible to everybody.
Yeah, it's visible, sir. Okay, yeah, it's visible.
I hope now the slides. Okay, so I hope the slides are also visible now.
Yes.
Okay, thanks. So let me begin this journey with you. As was already mentioned, the talk that I'm going to give today has a title, Sherlock Holmes meets Schrodinger's cat. The subtitle is actually more important, How the Quantum Can Keep Our Secrets. So this is a story about quantum mechanics, but it's more a story about something more perhaps romantic. Codes, ciphers, secret meetings, and so on. So to begin with, let's literally start with Sherlock Holmes. Frankly, I would have loved to read out the entire story to all of you, but I have only 40 minutes. and the story is not a very short one, but I'm pretty sure many of you have already read this story. If not, you should definitely. It is called The Adventure of the Dancing Men. And here, somewhere near the beginning, it goes like this. Holmes held up the paper so that the sunlight shone full upon it. It was a page torn from a notebook. The markings were done in pencil and ran in this way. So you had a bunch of dancing men drawn on paper, and somebody in whose house these markings had suddenly turned up had become alarmed and come to Holmes for help. Now, what Holmes says about these markings is something like this. I am fairly familiar with all forms of secret writings, and am myself the author of a trifling monograph upon the subject, in which I analyze 160 separate ciphers. This, of course, is Sherlock Holmes speaking, but frankly, it's more like Arthur Conan Doyle himself speaking. It's not really true that he knew 160 separate ciphers, but he was really an amateur code breaker. But I confess this is entirely new to me. But that was near the beginning of the story. By the time the story ends, it ends by Holmes writing a message in the same language, by cracking it first, to actually invite the villain of the piece for a meeting. And well, basically what is very important is the last line on my slide here. What Holmes says is what one man can invent, another can discover. Essentially saying that every code that is written by man can be broken by another one. So this was in the days of Sherlock Holmes. For the want of time, I'm skipping over the next part, which was a long discussion on Edgar Allan Poe's involvement in ciphers and how his stories actually talked a lot about cryptanalysis and actually talked about the actual theory behind analysis of ciphers and so on. But let me jump straight onto this theme of one man can invent, another can discover, and talk about a machine which produced code which at least its inventors thought were unbreakable. So this was the Enigma machine, which was used by the Germans in the entire Axis, the Axis people, to send coded message from each other. It was a very, very cleverly designed machine with many, many, many possible combinations, which could change from day to day, in fact, even from message to message, making this, as far as the Germans were concerned, completely unbreakable. And they believed till the end of the war that their code was not broken by the Allied powers. As it turned out, they were actually wrong about that. In fact, a huge team of spies and scientists collaborated to breaking the Enigma code, which was one of the major reasons why the Allies managed to succeed in the Second World War. One of the heroines of the story, this was a huge team effort, of course, but there are two people whose names perhaps should be mentioned more than anybody else's. The first one is a British spy. She goes by the name Vera Atkins. I'm not sure many people know about her today, but any of you who have seen the recent film, A Call to Spy, would actually have seen her in the role of the major spy master who sends Noor Inayat Khan and Veronica Hall to spy behind enemy lines in France. But this was, Vera Atkins' claim to fame really came before the World War began. Just before the fall of Poland, she managed to smuggle a copy of the Enigma machine out of occupied Poland, or almost to be occupied Poland, to her native Romania, and from there on to England. And it was the copy of this machine which gave people the first idea that this is something that people have to be able to decipher. However, even with the copy of this machine, it would have been impossible to break, except that there were huge, huge strides made in computation, in mathematical analysis of codes. And the one person who is perhaps best known for this is also the person whom we sometimes call the father of modern computing, Alan Turing, whose role in breaking the Enigma code has been, uh, well, has been immortalized in many novels, films, and so on. In fact, even recently there has been a new film called The Imitation Game, in which Turing is the central character. Now, I'm not going to talk a lot about Turing because that will entirely take away the entire time that I have. So I will move on to the next step. This, all I'm trying to ensure is or all I'm trying to drive home to you is that people have been writing codes or creating machines which produce codes for centuries, for many reasons. Used to be military reasons primarily at one time. Today it's more to keep our banking secrets safe. But the basic idea has been codes which can be written can also be broken. Now, quickly let us come to a code which is something which is almost behind most of cryptography that is done today. Almost all our banking transactions, etc., are protected by a code which is either this one or a derivative. This is called RSA. Well, actually, what is more important is RSA essentially started this trend of public key cryptography, which is what most advanced cryptographic systems use nowadays. The reason why it's called RSA is simple. It's just the names of the originators, Rivest, Shamir, and Adelman. And once again, there is a spy story at the background here. It so turns out that the RSA cryptography system was invented long before Rivest, Shamir, and Edelman came into the picture by somebody who was working in the British DCHQ, which is basically the British spy system for handling this kind of thing. And because it was developed under covert operations, it did not come to light before. So RSA gets the credit of discovering this system despite the fact that it had been known to mathematicians who were working for the British government a long time ago. Now, just to sort of set the stage a bit, I'm going to quickly tell you how a message is coded using the RSA. The idea is something like this. You have two players in the game and they're traditionally called Alice and Bob. And let's suppose that Alice wants to send a message to Bob. Okay. Now, any message, I'm pretty sure all of you are aware, can be converted to a number. If nothing else, the messages that you type into your computer are of course converted to strings of zeros and ones. So we can safely assume that any message is really a number. Let's call that number A. Now what Bob does is that in order to get a message from Alice is a receiver, Bob, who has to do some preparations. Now the preparations are as follows. First, Bob chooses two very large prime numbers, P and Q, maybe somewhere around 200 digits each. Okay. Now, of course, I'm not going to, I also want to give an example here, but I can't really give you an example involving 200-digit primes. That will be too large and simply not be very intelligible. So I'm choosing two small primes here just for the sake of example. Let's say P, the prime is 3 and Q is 5. So these are two primes. Now in actual applications, of course, these will not be as small as 3 and 5. These will be 200-digit primes. But the idea or the mathematics behind the thing works for small primes as well. Then what he does is chooses another number C, which is co-prime to the number P minus 1 times Q minus 1. Co-prime, let me remind you if you have forgotten, is a number which has no common factors with P minus 1 times Q minus 1. So what it chooses is a rather large number C, around 100 digits, as I said. But of course, in our example, it will be a lot smaller. In our example, P minus 1 times Q minus 1 is, of course, 8. So I have to choose a number smaller than 8, which is co-prime to it. So it does not have any common factors with 8. There are several choices possible. Well, not many actually, 3, 5, and 7. So let's say he chooses 3. Okay. So this is the beginning. And then he does one piece of calculation, which is he finds out the inverse of this 3 modulo p minus 1 times q minus 1. Okay, I need some cues from time to time to know that I'm still connected, because once I go full screen, I can't really see what's going on. So, Shataki, I hope if I get disconnected, you will call me and let me know.
Yes, I will do that. So far, it's fine.
Thanks. Okay, so the multiplicative inverse d has to be calculated. What that means is simply you find an integer which, when you multiply by c, gives you 1. Now, that may sound strange because no integer multiplied by 3 can give you 1. But we mean 1 modulo p minus 1 times q minus 1. That is, I want the number which, when multiplied by this c, in this our example 3, gives you 1 as a remainder when you divide by p minus 1 times q minus 1. And that's very easy to figure out. In fact, it needs a bit of number theory here, and many of you may be already aware of this. Number theory guarantees that in this situation, there is a unique multiplicative inverse within this set of all numbers from 1 up to p minus 1 times q minus 1 for a number c which is co-prime to p minus 1 times q minus 1. And it's obvious, and in this case, it's rather easy to figure out. You can easily calculate this and show that this is actually 3 in this case. Again, this 3 happens to be the same as c. So in this particular kind of mathematics, 3 is self-inverse modulo 8. Just to check, if you multiply 3 by 3, you get 9, which is of course 1 modulo 8. Modulo means just take the remainder. So this is the preparation that Bob has to do. And what he does after that is that he tells the whole world 2 numbers. One is the product of the 2 primes he has chosen, n, which is pq, and c. These 2 numbers are given to everybody. So maybe he writes them out in a telephone directory or something. Actually, nowadays it's written on, not written, but it's stored in his computer. And anybody who wants to send him a message can actually easily find out what this pair is. So this is called Bob's public key. Public because it's known to everybody. Everybody knows this. There's nothing secret about this. So how does Alice send a message to Bob? Okay, one important point. Bob has to keep D, the multiplicative inverse of C, private. Okay, in this case, D of course happens to be the same as C, but he does not disclose the value. He keeps the value to himself. Now, when Bob is to receive a message from Alice, what Alice will do is something like this. Let's say Alice's message is 7. That's again an example. Of course, the real message will be a lot longer. So first, she will have to look up Bob's public key. So she will have to find out the pair of numbers n and c from a public directory somewhere, maybe on the internet. So in our example, Bob's public key is 15, the product of p and q, and c, which is 3. So this is Bob's public key, which Alice will use. So what she will do is raise a, her message, to the power c, and do it modulo n, right? So in this case, he will raise 7 to the power 3 modulo 15. So 7 to the 3 direct calculation shows is simply 343, and you throw away 15s and just find out the remainder after that. It's easy to see that the remainder is 30. 330, of course, is divisible by 15. 13 is the remainder. So this B becomes Alice's message. So simple. Take your actual message, which is the so-called plain text, the thing that you want to send, raise it to the power of the second power C, which is a part of the public key, but do it modulo n. So you use both parts of Bob's public key to do this. And once you have created the message, you just send this message, which is called the cipher text. So 7 was a plain text, the message that she wanted to send. D here, namely 13, is a ciphertext which gets sent to Bob. And now Bob has to decode it. So how does Bob decode it? The answer is simple. Bob must calculate B to the D modulo n. Remember, D is something which Bob kept to himself, did not disclose to anybody else. So all you have to do is get Alice's message, raise it to the power D. In this case, of course, D happens to be the same as C, but that's just a coincidence. So what he has to do is he has to raise 13 to the power 3 modulo n again, modulo 15. So 13 to the 3 is 2197, straightforward calculation, but you don't really have to calculate it do this long calculation anyway. There are tricks which can reduce the size, but the important thing is when you take the remainder of 2197 with respect to 15, the answer is 7, which is the original message. So this is how RSA works. Of course, RSA actually works with much larger numbers, but this is the basic idea. Okay. So now, note the important thing is, why is this such a big deal? Why does anybody care about RSA? This seems like a very simple piece of mathematics. The important thing is it's asymmetric. Encoding here is done via public key, so that anybody who knows your public key can send you a message. Funnily enough, once somebody has encoded the message, that person will never be able to decode it back. So if you have written a complicated message, encoded it, and then deleted your original message, you cannot get it back from the ciphertext unless you know the secret key which Bob has. Decoding is done by a private key. So encoding via public key, decoding via private key, and as long as Bob knows the private key and nobody else does, there is no problem. Only you, meaning only the person who is actually meant to read the message, can read the message. Now, the real question is, this whole process seems to be rather trivial, right? All the world knows N, which is the product of P and Q, and C. Of course, how do you calculate the private key? All you have to do is find out the multiplicative inverse of C, which everybody knows, with respect to P minus 1 times Q minus 1. Now, everybody knows the product of P and Q, just 2 primes multiplied together. Why can't we calculate D from this, from whatever everybody knows? We could, of course, if only we had the means to factorize N to find out P and Q. Now, this might surprise some of you, because from our childhood, we have learned how to factorize numbers. But I'm pretty sure as a child, you found factorization difficult. And maybe you got scolded for that by your teacher. I don't know, I found factorization difficult. But it turns out the factorization really is horribly difficult. It's a very, very hard problem. Okay? So current record of the largest semi-prime. Semi-prime is the product of 2 primes. The current record until very recently, I guess this is still the current record, is a number called RSA 250. It's a 250-digit semi-prime which was factorized in February of 2020 by a big team of mathematicians. In fact, the last name here, Paul Zimmerman, is one of the authors of a major cryptographic system, very similar to RSA, but different from it. And the previous record, RSA 240, took 900 years to factorize. Of course, it didn't take 900 years. It would have taken 900 years if we had used a single 2.1 gigahertz Intel Xeon Gold CPU, which was quite the state of the art at that time. The reason why they could still do it in a reasonable amount of time is that they pooled a lot of computers together, used parallel programming, and managed to factorize this. But the important thing is, the best algorithm we have today, at least we have today for classical computers, is something called the general number field C. And this takes roughly into the 1/3 step to factorize. And I'm simplifying things a bit here. And so, if a 200-digit number, if it takes only days to factorize with today's technology, the kind of numbers that are actually used in RSA. Remember, the products of two 200-digit numbers, so roughly 400-digit number, would actually take around 10 to the 62 years, way more than the age of the universe, to factorize using current state of the art. So, although it's possible in principle to crack RSA just by factorizing n, given the size of the numbers that are actually used, this is next to impossible. And it's next to impossible in standard amount of time. Now, one person actually showed us a way of being able to actually solve things like this, to be able to factorize very large numbers or solve other problems which classical computation finds impossibly hard to do. And like many other wonderful things in physics, Feynman got there first, and Feynman was talking essentially about trying to simulate natural processes using computers. And there he had this idea that if you want to really simulate natural processes, which are quantum mechanical in nature, what you really need is to harness the power of quantum mechanics to do the computation. You cannot really handle nature properly by using classical computers. You need the power of quantum computation. Well, the basic idea behind that was laid a long time ago by Erwin Schrödinger, and I'm pretty sure most of you know this beautiful equation, which is the central equation of all of quantum mechanics. But the reason why Schrödinger's name is more important for us is another thing which almost everybody knows about. In fact, that was part of our title, the Schrödinger's cat. In an article published in 1935, I'm not trying to make a fool of myself and I will not try to pronounce the German name here, but it's not really very difficult anyway. But still, in this article, he described his famous thought experiment in which he talked about a cat which, under the circumstances of the experiment, could be thought of as in a superposition state of being dead or alive. Those of you who do not know about Schrödinger's cat, please read up on it. It's one of the most fascinating things in modern science. But the important point is, you can have systems which can be in superpositions of two different states. And today, what we do is harness the power of this kind of quantum superposition, and we are trying to make practical computers using that. So what we deal with are things called quantum bits. You know that bits are basic units of computing. They can either be in a state 0 or in a state 1. The quantum bit can be in a superposition of two states at the same time. And because of this superposition principle, quantum computers which directly use these quantum techniques, they have immense computing power. Well, immense computing power, provided you can harness that properly, is really a difficult thing to do. But one of the important results which came out of quantum computing very recently is that quantum mechanics became a threat to the RSA, this RSA cryptographic system, which, remember, is at the heart of almost all our cryptography today. So all banking, all diplomatic transactions, everything could be threatened if you could break the RSA code. Well, the person who was instrumental in that is somebody called Peter Shor, who gave us an algorithm using a quantum computer. Okay, I'm not going to explain this quantum circuit to you. This is standard part of quantum information theory course, Shor's algorithm. I'm not going to explain this simply because this would take me at least 2 lectures to cover, if not more. In fact, it will take me more because I will also have to give you the background. But the basic idea is you can build up simple quantum systems, which in the end of the day will be able to, with a very high probability, give you factors of an input number. And along with his wife Jennifer and Peter Shor sort of advertised this in the form of a limerick, which went like this: if computers that you build are quantum, then spies of all factions will want them, our codes will all fail, and they will read our email till we have crypto that's quantum and don them. By the way, this was announced in a actual scientific conference. This particular limerick was read out, and in that very conference, Volker Strassen replied to another limerick. So quizzes do have fun. They are not all very serious types. So Volker Strassen wrote, to read our email, how mean, of the spies and the quantum machine, be comforted though they do not yet know how to factorize 12 or 15. That was because at the time when Peter Shaw wrote this, the biggest quantum computer that could be built could only handle numbers as small as 12 or 15. In fact, not even that. But this was 20 years ago. Today's quantum computers have advanced a lot. At least the public ones that we know about can handle up to 20 qubits. So numbers of the size 2 to the power 20, which is still a long, long way from a 400-bit prime, which we need to be able to crack RSA properly. But with rapid advancement of technology, the day is not far when quantum computers become strong enough to seriously challenge RSA. At least that's a fond hope of anybody who is in this business. One of the major goals would be to be able to build a computer that is strong enough to threaten all cryptographic systems in the world. In fact, conspiracy theories would have you believe that has already been done. Somewhere or the other, some government, maybe the US government, or maybe even our own government, is reading our emails by cracking RSA and not letting everybody else know. But that's unlikely. However, the important point is this. The quantum here taketh away our power of coding, but it also giveth. That's a biblical quote, in case anybody missed that. Well, okay, let me just maybe, how long do I have at this point?
You have another 25 minutes for sure.
25 minutes, that's great. Okay, thanks. Okay, I hope this is not going too fast, or I'm actually going a bit fast, but I hope this is okay. Anyway, so the point is, if long ago we had found out that there is one cryptographic system which is completely unbreakable, and it was found out long before quantum mechanics came into the picture. There's something called a Vernam cipher, named after the person who first talked about them, and they also go by the name one-time pads. The basic idea is two people, the one who wants to send the message and the one who wants to receive it, will both have a one-time pad that is identical copies of the same pad, full of random numbers. Okay, the one which you can see on your screen does not have numbers, it has letters, but basically the same idea. This is an actual one-time pad. It was used in actual spying one time. So the basic idea is, for one message, you use the top sheet of your pad. You write your code using that. When you send the message, the receiver has an identical copy of the pad, so he knows exactly what code you used. He uses that to decode. The important point is this code is completely random. So if somebody else does not have a copy of the pad, that person will never be able to decode this message. So this is a provably secure system, in the sense that there is no way anybody who does not have the key, this access to this one-time pad, will be able to actually read these messages. So let us just give a quick view of how people can use this. So instead of letters, we are using random numbers, and let's just say random binary numbers. That keeps things simple. The key is some random string of numbers which both our protagonists, both Alice and Bob, share. So Alice has this random key 1000110111. Bob happens to have an identical copy of that key, when nobody else presumably does. Okay. So this key has to be at least as long as the message that is being sent. Now the message, as I said, has to be a number. So Alice writes out a number in binary again, just below the key. And what she does then is uses something called XOR. I'm sure most of you know what XOR is. It's the exclusive OR that people study about in Boolean algebra. The important point, okay, the basic definition is wherever the key and the message differ, that is, key is 1, message is 0, or key is 0, message is 1, the output is a 1. Whenever the key and the message match, the output is 0. So here the ciphertext will be something like this. The first 2 bits, key is 1, message is 0. So cipher is 1. Then your key is 0, message is 0. The output is 0 because both match. Then you have 1. Then you have 0, and okay, you can easily read off the rest of it. So this is how this encryption is done. It's done by using something called bitwise XOR. Every bit is compared of the key is compared to a bit of the message, and you get the cipher. How do you decode? Decoding is done exactly by using the same method. So Bob sends a coded message over something called an open channel. That is, Bob does not try to keep the cipher text a secret. He can even print it on today's newspaper. But unless somebody has a key, there is no way you can make sense of what the ciphertext actually means. But remember, Bob receives the key, receives the cipher message. He also has a copy of the key. And the way in which the decoding will work is simple. You just take the key and the cipher and do bitwise XOR again. So 1 and 1 gives you 0. Remember, this is 1, that gives you 0. Then 0 and 0 gives you 0. 0 and 1 gives you 1, and so on. And you can easily check that the decoding process has given you back the message exactly. And that's because of a very simple property of the XOR operation. A XOR B, XOR with B, is actually back to A. This is something which can be a nice exercise for people who know Boolean algebra. It's a trivial 2-line calculation. That XOR actually is self-inverting. So once somebody has a key, he can easily break the cipher and go back to the original message. But if you do not have the key, then you have no chance, because the key could be any one of the random strings of zeros and ones possible. Okay. So an eavesdropper, somebody who has learned what the cipher message is, maybe the cipher message is printed on today's newspaper. I can just take it. Anybody can look at the newspaper and know what the cipher message is. But if I don't have the key, I have no chance of deconstructing what the original message was. So now the question might come, if this is so simple, and if this has been around for a long, long time, what has quantum mechanics got to do with it? Actually, just a bit. Let me just try to explain that. There is one problem with the one-time pad, however. Though it's probably secure in the sense, it's only secure if something happens. Two parties must share a common pad, and now delivering the pad and keeping it secure, ensuring that nobody takes a look at it and finds out what is written there, becomes a major issue. Especially if this is wartime and you want to send a message to somebody behind enemy lines, getting the key to that person would be difficult because it has to be done physically. Now, extraordinary measures have been used for this. People, for example, have rolled up one-time pad pages in a walnut kernel and sent that again. In fact, this is again a genuine picture of something that was actually used in warfare. But the important thing is to be secure, the key has to be known only to legitimate parties and used only once. If the same key is repeated over and over again, then by standard cryptographic techniques, you can actually break the message rather simply. So the whole point is one message uses one key, the next message will use another key, which is why you have to have a ready supply of keys one after the other. In fact, reuse of the same key by the Soviet intelligence allowed American Venona project to decrypt many messages during the Second World War and during the Cold War. By the way, despite the fact that Russia and the US were on the same side in the Second World War, they actually kept on spying on each other during that time. And of course, this continued into the Cold War. Most of the people in the Venona project were women because they were the ones who were who supposedly had enough concentration to be able to do the hard work involved here. Anyway, what do we need really for this one-time pad to really succeed? What you need is a way to securely distribute a random key between two legitimate parties, and to ensure that an eavesdropper should not be able to intercept the key, and any attempt at doing so, any attempt at intruding into this process should be detectable. That is, if somebody has managed to look at the key, or even try to look at the key, this attempt should be something which can be detected by both parties, so that they will not use that particular key any longer. But this is where quantum mechanics gives us a way. And this very often is called quantum cryptography, but it's not. It's actually quantum key distribution. The only thing that quantum mechanics does here is allows you to pass the key from one user to another without possibility of intrusion. So it's really QKD and not quantum cryptography, although quantum cryptography is the popular name. Now, I will skip some of the history because I am short of time, but basically, Stephen Meissner came up with some of the basic ideas here, and based on his work, which was published only in 1983, two people, Charles Bennett and Guy Brassard, proposed the first quantum cryptography protocol. As I said, this is really quantum key distribution, but it's called quantum cryptography. And this was called the BB84 protocol simply because B and B were the two people's names, Bennett and Brassard, and 84 from the year 1984. Well, this was at a theoretical level, but in 1989, Bennett teamed up with Leo Smolin, and they actually produced the first experimental distribution of quantum key distribution using the setup that you can see on your screens right now. More advances occurred. So Arthur Eckhart, for example, came up with another protocol which uses another very, very important concept in quantum mechanics called entanglement. This is a whole story in itself. Could be several lectures, but I'm not going to go into that right now. What I'm going to describe to you is a protocol which Bennett came up with. Charles Bennett, the same Bennett as in Bennett and Brassard, but he came up with it again with another one in 1992, a simpler one. It's called the B92 protocol. The picture you can see here is actually Eastern Zonal Cultural Center in Calcutta, where a few years ago Bennett had come, before the pandemic, of course, to give a lecture. So here you can see Bennett speaking to a few of my colleagues. Okay. So using the B92 protocol, let me just quickly try to describe this protocol to you. Again, Saptakit, how long do I have now?
Another 12-14 minutes.
Okay, good. Using the B92 protocol, two friends, Alice and Bob, can establish identical random keys. This is the basic idea. The keys have to be exactly random, but the key which Alice has to be the same as the key which Bob has. And if somebody else, who is traditionally called Eve in this business, no disrespect to women here, but eavesdropping, Eve, that's the nomenclature that's used. If Eve tries to intercept the key, she will not be able to recover all of it. Number one, she can only at best get a part of it. And more importantly, the two friends involved here will be able to detect that she has actually tried to intrude, and hence will not use that key any longer. So the basic physics which is used here is something which almost everybody knows. If you have two polarizer sheets which you keep next to each other, one of them you call the polarizer, the other you call the analyzer. I'm sure most of you know that as one polarized sheet is rotated with respect to another, the intensity of the transmitted light changes from high to low, and when they're exactly at right angles, no light goes through. Okay. The explanation for this is also simple. Light is a transverse electromagnetic wave. If you look at the electric field vector, once it passes through a polarizer, the electric field vector is horizontally polarized. That is, it oscillates only in the horizontal plane. That is along one plane, which is shown here. Now, The other Polaroid, which we call the analyzer, has something called a path axis, which and only the component of the electric field vector along the path axis gets transmitted. So as the Polaroid is rotated around, this component changes. Of course, the bigger the angle, the smaller the component. And that's why less of the electric field vector gets through. And since the square of the electric field is proportional to the intensity, E, of course, is E0 cosine theta. And I, the intensity, is proportional to square of that. So it's given by I0 cos square theta. This is a familiar Malus law. In particular, for diagonal polarization, that is when the analyzer is at a 45-degree angle with the polarizer, cosine square 45 degrees is half. So 50% of the light intensity passes through the polarizer-analyzer combination. So that's something which is basic physics. I think everybody who has done class 12 should know this much. And of course, when the angle is 90 degrees, I becomes 0. So no light goes through. So this is familiar application of the wave nature of transverse wave nature of light. By the way, by another happy coincidence, today happens to be the birthday of Maxwell. I don't mean Glenn Maxwell, of course, that's in October. I mean James Clerk Maxwell, the person who gave us the wave theory of light, among a unification of the ideas of electromagnetism. So it's rather nice that I'm talking about this on Maxwell's birthday. But anyway, Maxwell's theory, which was classical, gave us a very nice understanding of Malus law. All you have to do is look at the component of the electric field vector, and the component tells you why the intensity is getting smaller as you rotate the analyzer. However, how do you understand this in terms of the quantum theory? In quantum theory, light is a stream of photons. And photons, for example, when you have a 45-degree angle between the analyzer and the polarizer, light intensity cuts by 50%. Does this mean that the photons break up and only half a photon goes through? Of course not. Photons cannot be broken up. So what happens is when you pass this through this 45-degree or pi by 4 combination, it's not that the photons break up in half. Roughly half of the photons go through. The other half gets blocked. So energy of a given photon doesn't change, but half of the photons are coming through. So the energy that you see on the other side becomes one half. Now, this is an inherently quantum mechanical process in the sense that you can never say for sure which photon is going to go through, which photon is not going to go through. Okay? But once you send a stream of photons, you will find at the end of the day, half of them will go through, half of them will get blocked. So when even if you send them one photon at a time, all you can say, when they're coming in all at a go, you can say half of them go through. But what happens when one of them comes in? All you can say here is that the probability of a single photon coming in is 50%, going through is 50%, and getting blocked is 50%. And that's it. Nothing more can be said. Quantum mechanics doesn't allow you to say anything else about what will happen in a given photon. But what it gives you is a statistical picture here. So this is an entirely random process. No prior prediction is possible for a single photon. And the ones which go through actually change the state. Now that's also easy to understand because after it goes to the final polarizer, what comes out is polarized along the path axis of that polarizer. So in this case, if the incident photon had a horizontal polarization, the one which comes out has to have a 45-degree polarization. That's it. So this is the polarization version of what is called the collapse of the wave packet. You had all possible directions as a possibility, but once you go through the polarizer, it can only come out in one particular state. Measurement of the state of the polarization by the polarizer has made the wave packet of the photon collapse. Okay, this is less dramatic than the wave function collapsing at a single point, but basic physics is the same. Now, how do we use this very simple quantum mechanical principle to actually send coded messages? Again, not coded messages really, but keys. So in the B92 protocol, what happens is, Alice and Bob generate two independent random strings of zeros and ones. So they are sitting on the computer, they have asked the computer to produce long sequences of zeros and ones, independent, completely random. Okay. So there is very little chance that they will come up with the same sequence. In fact, you can easily figure out there's a 1 in 4 chance that a given bit will be the same. Okay. Sorry, 1 in 2 chance of that a given bit will be the same, and a 50% chance that they will be different. Now, what Alice does is Alice uses her random string of bits to send a polarized photon over to Bob. So what she does is, if her bit is 0, then she sends the photon polarized horizontal. Okay, as you can see here. And if her bit is 1, she produces and sends the photon which is polarized diagonal. Okay, so that's Alice's job. Bob's job, on the other hand, is setting up an analyzer through which the photon will pass. And what Bob does is sets his analyzer according to his string of random numbers. So if his string of random numbers shows 0 at a particular position, for that time, what Bob is going to do is use a diagonal pass axis. He will set his pass axis of the analyzer diagonally. But remember, this diagonal is 90 degrees to the diagonal state of polarization which Alice set. And when Bob's bit is 1, he will set a vertical polarization. He will set the analyzer with the pass axis vertical. Now this seems a bit strange because remember, Alice bit 0, horizontal polarization. Bob bit 0, pass axis set diagonally. Alice bit 1, sends the photon with the polarization which is at 45 degrees. Bob bit 1, sends the polarization which is vertical. The important point you should realize is, if Alice had a 0 and Bob had a 1, then Alice would send a horizontal polarization, Bob would set his polarizer or the analyzer vertically, which means Alice's photon will definitely not go through. On the other hand, if Alice had a 1, Bob had a 1, Alice would send a diagonal polarization. Okay, Alice had a 1 and Bob had a 0. Let's take a look at that first. Alice had a 1, Alice sends diagonal, Bob has 0, Bob sets his pass axis perpendicular to that diagonal. Again, no chance of the photon going through. On the other hand, if both of them are 0, Alice sends horizontal photon, Bob sets up his pass axis at 45 degrees, at 135 degrees actually. So what happens now? Now Alice's photon has a chance of going through. 50% chance, but a chance nonetheless. Okay? So what they are going to do is just play this game. Alice will look at her bits one by one, and according to the way her bits are set, randomly generated by the computer, she will produce polarization states of the photon, send them over to Bob, and Bob will analyze them using analyzer settings which are again dictated by his random pair. The all important point is, whenever the two of them have different bits, 0 and 1 or 1 and 0, there is no chance whatsoever of a photon getting through. Only when they have the same bits can the photon go through. Even then, there is only a 50% chance of it going through. But then, that's fine. That 50% chance, half of the time, they will have the same bits. Half of that time, the photon will go through. So 1/4 of the time, they will be able to agree that, okay, Alice and Bob had exactly the same bit. So what they will do is simply, okay, I have a basic table here which essentially shows that, what I was trying to say. But the important thing is this. If a photon goes through, they know they have the same bits, so they will retain that. If it doesn't go through, they do not know for sure whether they have a different bit or they could have the same bit. There's a 50% chance which blocked the photon. But even then, they will safely discard that. The photon will never pass if Bob and Alice have different bits. And by keeping the bits at which the photons get through, they can share identical random keys. Now, all Bob has to do is publicly declare which photons went through. After doing all this, all Bob has to do is go on the radio, for example, and tell everybody in the world that, okay, position number 1, position number 13, position number 17, position number 18, these photons went through. And then what he will do is keep those bits. Alice, who has got this message over the radio, will again keep the same bits for us from her string. And now both of them have exactly the same pair of same bunch of random bits. So quantum key distribution has been completed. Now it will take some time to analyze why there will be a problem if why Eve, who will try to listen into this, maybe intercept the photons in the way and try to figure out what the key is going to be, is going to run into trouble. But I think I've already told you enough for you to be able to figure that out yourself. Exactly why anybody who is trying to sit in the middle will have a problem. Okay, I can take up this in the question answer session if we have one, but I will just skip this part because I'm definitely sure that I've run out of time. But the important thing is also
Dr. Dasgupta,
yeah.
You can just go on with your pace if you need a few more time, because I have already talked to the other speakers, so they're fine with that. Okay. Everybody wants to hear you, so no problem with that.
Okay. Good. Then I will tell you a bit more about this.
Yes, please. Okay.
So now remember what we have done is this. Alice and Bob had the string of zeros and ones, completely random to begin with. But from that, they have been able to cull out exactly those bits, some of those bits which match. Of course, 50% of the bits which match, they have missed because the photon did not go through. But that's fine. If they want, say, to have a string of, say, 1,000 bits, they'll start with more than 4,000 to begin with. In one half of the cases, the bits won't match anyway. In the other half, the bits will match, out of which half will go through, half will not. So they will end up with a 1,000-bit long common code. But what if Eve intercepted the photons midway? Alice is sending the photons to Bob. Suppose Eve is sitting in the middle and trying to do this, trying to find out what's being sent. So she will also have to determine the state of the intercepted photons, right? The problem with her is she has no clue about either Alice's random bits, because that's only on Alice's computer, or Bob's random bits, because those are only on Bob's computer. So the best she can do is she can try to mimic Bob without really having access to Bob's random bits. She can only create her own random bits and use that. So she can be now. The problem is, now that she creates her own entirely random string of bits and tries to set her analyzer using that, she can be sure of the photon state only if it passes through her analyzer. Right? So if it passes through her analyzer, she knows, and her analyzer was set at vertical, then she knows that it must have been diagonal, because the horizontal one will never pass through, and so on. Now this will happen 25% of the time. Again, essentially the same reason why 25% of the time Bob was successful. Now in these cases, she can only just set the photons, let the photon go along to Bob, nothing else. She doesn't have to do anything else. She has found out the state of the photon, and then either if she has destroyed the photon in the process, she can create a new one in that state and send it along. Not a problem. But in the other 75% of the cases, she does not know what state was really sent. She does not know whether what was sent was a diagonal one or a horizontal one. Remember, only if it goes through are you sure what it is. In the other case, she has to guess what it was. Okay. Remember, if she cannot just observe the photon and stop there, because if the photon does not go through the Bob, they will not be creating the key, so no point in learning what the key is if the key is not being created. More importantly, Bob and Alice would know by the fact that they are missing some photons that somebody is doing some hanky-panky sitting there. Okay. So what she has to do is guess the state. She has no clue what it is, but she has to guess what it is, prepare a copy, and send it along. Now, this is the mathematics which is very simple probability theory. So I will urge all of you to try to figure this out. By doing all this, she can be at best sure of only 1/16th of the actual key. But 1/16th of a whole key, if the key is actually used, is quite a lot. In that, knowledge of less than that part of a key has enabled clever cryptanalysts to break actual codes. Okay, wars have actually been won on less than a 1/16th of a whole key. But the important thing is Alice and Bob now share a key which is partly compromised. Part of it is known to Eve. But what saves them is not that Eve can learn only 1/16th of the key. What saves the day for them is Eve's actions leave a signature in the final key. Remember, 75% of the time Eve had to guess what was sent. Right? So out of that, since she's only guessing, she will get it right half of the time, wrong the other half. So she will make mistakes in the guess. That means that while Alice has sent a 0, Eve might have sent a 1 along. Now Bob, on the other hand, may have said a 1 and got the photon to pass through. So what will happen is, in the end, the two keys will actually have errors. Alice and Bob's keys will not exactly match. And this happens because of the collapse of the wave packet. Eve's measurement of the photon state actually changed the state of the photon. So now she has only to get, she can only guess what the state was before she measured it. So this error in the final key that Alice and Bob decides upon can be found out very easily. All they have to do is randomly take out a portion of the key that they have. Remember, if Eve is not sitting in the middle, then Alice and Bob will end up with an identical key, right? But with Eve's intuition, there will be several errors. Now, all Alice and Bob has to do is randomly share a part of their code, again, over open channel, maybe printed in a newspaper advertisement. Now, once that happens, they can check whether the part that they have shared are identical or not. If they're not identical, there may be some small errors because of transmission problems. A photon may be misidentified sometimes, but these things can be easily estimated. What is the probability of that? So if you get many more errors in the shared key than actually should be there from random errors, Alice and Bob would be sure that somebody is listening in, somebody is doing some hanky-panky, so they will not share their key. They will not use the key any longer. So only once they are sure that the shared bits are error-free, they will of course not use the shared key bits any longer, right? Because that's openly known. But they had a long key out of which they have shared a random part. They've just verified that those random parts actually agree. And once they're comfortable that there is no error, they can discard the shared part of the key, and use the rest of the key for actual coding. Now, there's another issue that might strike some of you. After all, the real problem with Eve's situation is that Eve has to guess what the state is. If the photon passes through her polarizer, Eve knows exactly what the state is. If it doesn't pass, she has no clue. But couldn't she make a clone of the state before actually doing the experiment? If she could, then life would be very easy, because then she could do this at her leisure, just clone it, send one clone to Bob, that will be identical to whatever Alice sent, don't do an experiment on that, do an experiment on the other clone. Now, it so happens that quantum mechanics has a very interesting result which says no. The basic idea is anything in quantum mechanics which is non-disruptive, which does not disrupt the state of the photon, has to be unitary. There's a mathematical term, I'm sure many of you already know what this is. And there is a standard theorem in quantum mechanics, which is not there in our undergraduate courses, simply because our undergraduate courses are not geared towards this. But such unitary operations cannot clone non-orthogonal states. This is the so-called no cloning theorem, which is at the heart of quantum information theory. The proof of this theorem is actually really trivially easy. It's much easier, for example, than most quantum mechanical calculations that our students do routinely. But anyway, the important thing is cloning simply cannot be done. And that tells us that Eve has no way of cloning the thing and then sending it over. So Eve's presence will always be detected. Now, so far I've just given you this basic theory behind this. There are lots of refinements on this, ways of detecting, refining codes, making it even more error-free and so on. And there have been attempts at breaking these codes using other protocols and so on, and attempts to refute them. That's a whole new subject. It's one of the most important, well, not most important, but a very important modern application of quantum mechanics. But let me just tell you that this is not just theory. In fact, in 2009, a collaboration between universities of Cambridge and Toshiba achieved secure key distribution using quantum protocol at 1 megabits per second, which is fast, over 20 kilometers of optical fiber. This has come a long way from Leo Smolin's experiment, which was done on a tabletop. In 2017, a Chinese team achieved key distribution by entangled photons over 1200 kilometers. So that's a big distance. In fact, there is a space mission which actually established a quantum key distribution channel between China and the Institute for Quantum Optics and Quantum Information in Vienna in 2017. So this was done over a huge terrestrial distance and done by bouncing the signal off from a satellite. So it went out to outer space and came back. So you can see that you can actually communicate secure keys over long distances using this. And it's not just, these are of course done in the lab, but this is not confined to the lab. In fact, the first bank transfer of money was carried out in Vienna as long back as 2004 using QKD. And not only that, in the Austrian 2007 national elections, the results were transmitted to the national capital using quantum encryption. So this has already been used in real life scenarios. In fact, as far as I know, today 4 companies offer commercial quantum key distribution kits. So this is no longer an esoteric thing which somebody only studies in some theoretical fashion or does just research it. This is actually real world application now. In fact, many more companies are actually trying to join into this venture. So QKD is not the future, it's already the present. That's all I really wanted to say. This picture is of the picture in the background is of this particular bouncing thing. Okay, for those of you who are interested in the Edgar Allan Poe story, which I did not have time to touch upon, the Edgar Allan Poe digital collection is a wonderful collection which many of you can take a look at for the kind of beautiful stories using cryptography as well as his actual dabbling with cryptanalysis. And that's all I have for you. Thank you. And thank you for listening to me for so long.
Thank you so much, Dr. Dasgupta. That was a very nice talk. Starting with the Allison problem, just went long way, and few of the things I understood, few of the things I didn't understood. So you said that quantum cryptography is not the correct word to describe this thing. Like you said something quantum key something. I just missed it.
The term actually is quantum key distribution. Cryptography is the process of creating a code once you have the key. Okay, strictly speaking, cryptography is taking a text message and creating the code out of it.
Okay.
That's cryptography. Quantum mechanics has no role to play there. What quantum mechanics actually does is quantum key distribution, in the sense that the key which is used to create the coded message, that has to be shared by 2 parties, and this sharing is done using quantum mechanics in these protocols.
Okay.
So what is being shared here Note that you started with an entirely random string of numbers and you discarded some of them to end up with a common random key. A random key, of course, is not a message, right? So by the end of the process, all Alice and Bob have are a bunch of random strings of zeros and ones, identical bunches. The important thing is using that, Alice can encode her message, send it to Bob over an open channel, not caring who listens, and Bob will be able to decode it using his key. There's a key distribution part which is done using quantum mechanics. That's
Okay.
QKD.
And that was nice. The thing where you just continued with that polarization example and then putting that on the Alice and Bob problem.
Yeah,
So,
but
but
the
anyway,
polarization actually is used in a big way. Quantum optics is used in a big way for this.
yeah, yeah.
Not the only way, but one of the major ways.
Yes. Okay. So there are many questions. So Dr. Saurabh Haldar from Maths department is an assistant professor there. So he is going to um, look after the question answer session. So Dr. Haldar, can you just read out the questions to Dr. Dasgupta?
Yes, thank you, Dr. Kaur, and also a very interesting talk on another interesting topic. So, thanks to Dr. Dasgupta. So, we have a few questions from the viewers. As there is a time protocol, so I just want to mention some of them. So, first, the question from Mr. Anupam Banerjee. The question is how a message is transformed to number.
Okay, how a message is transformed to number. There are many ways, but for example, one of the simplest things would be you would be printing A, B, C, D, E, F, G, H, right? But A, B, C, D, E, F, G, H all have their ASCII codes in a computer. So when you type out A, B, C, D on a computer, what is actually used are numbers.
Okay.
So that's one way. There are many other ways, but that's really not important. The important point is conversion to number can always be done. You can do something as trivial as assigning a number to each letter, or you could do something more sophisticated.
Okay, he has made another query that is there some probability that we can decode the message from cipher without key using Boolean algebra?
Not Boolean algebra, but there are, because if you are talking about Boolean algebra, because I talked about XOR, you have to realize one thing. If you are using a one-time pad, you have a totally random key, right? And that means that any of the random keys with the same length are all equally likely. And if you use a different random key, you will end up with a different decoding. That is what I said. What I meant when I said one-time pads are provably secure, in the sense that all messages of the same length are equally likely decodings. If you have a coded message with say 200 characters long, it could be any of the 200, any one 200 character message that you could think about. Because all you would have to do is change the random key and you get another version. Okay. Now, if you, on the other hand, if you use the same random key over and over again, which is why these are called one-time pads, you use them only once. But if you use them over and over again, then certain patterns start to emerge. You don't have to use Boolean algebra there, but things like frequency analysis, linguistics. For example, you know E is the most common letter in the English language. So by looking at which patterns keep on, and TH, for example, is a very common diphthong pair. So by looking at such patterns, you can actually decode quite a lot of the message. And then, of course, usually from the context, you know what the message could be about. Okay. So using all of that, for example, one part of cracking the Enigma code was the German operators had this habit of sending good morning at the beginning. So the British guessed that this part of the message must mean good morning, and then use that to try to learn a bit more about the key. Surprising pieces of information can be obtained. If anybody is interested, I would strongly suggest reading to begin with Simon Singh's book, The Code Book, which is a beautiful description, which is a beautiful description of this process at a very readable level. And then there are, of course, very technical books on cryptography and cryptanalysis. Strongly mathematical books, of course. It's a very important branch of mathematics and probability theory here.
Okay. So one more question is, in Eckhart's protocol, the operators used by Eckart is valid for any entangled state or for particularly singlet and demerged state.
Well, actually, that's a bit of a problem. I don't exactly remember Eckhart's protocol right now.
Okay.
I studied that long time ago, so I've forgotten. So sorry, I can't answer that. I'm pretty sure this information is available openly everywhere. You can just try looking at Wikipedia, for example.
Okay, sir. There is question from Sudipta Viswas. How the alphabets in messages between two parties converted into these codes?
As I said, you can do it many ways, right? But the important point is you could just say A stands for 0, B stands for 1, or I don't remember, but A stands for 32, I guess, in ASCII, small a, or 61. I don't remember which one. But anyway, you could convert letters to numbers by just starting with a well-defined set. Any mapping will do, as long as everybody agrees about the mapping. That's it.
Okay. From Mr. Tanmay Das asked that in today's life we used internet to communicate to computers. How do quantum computers communicate?
Quantum computers don't. The point isn't really communication so much. You want to communicate only because you want to get information from one place to another. Quantum computers are essentially used to do computation part of it. Communication actually is a bit of a problem for quantum computers because one of the major problems with quantum computers is decoherence. External environments tend to do harm to their computing process. So most quantum computers are isolated, very, very securely placed in very low temperatures and so on, so that random thermal motions, etc., will not disturb them. So communication, of course, basically, look, when you want to write code in a quantum computer, you use basically standard quantum computing language. By the way, if anybody is interested in quantum computers, you can find lots of resources on the net, and you can even use your own quantum computer. IBM has this quantum experience experiment which you can join, create a login, and you can write codes on quantum computer, run it yourself, and see what the result is going to be.
Okay, so one question is there, what is free space quantum communication?
Free space quantum communication is the kind of example that I gave at the end.
Okay.
Typically, most quantum communication is used using, say, photons in a given state, either polarization states or entangled states, and that's usually done over optical fibers. But free space is where you transmit photons over in vacuum, let's say, not using optical fibers.
Okay, and one question I can see from Arijit Mandal that can no cloning theorem explain PNS attack?
Explain what?
PNS attack.
Well, explain, you mean avoid, right? That is, why does an attack fail? Well, yes, in a way. Not exactly. There is more to that than this. That's a very technical question, so I don't really think I can answer that here.
Okay. I can ask one more question last. So from Sanjukta Pal, that naively, the one-time password we get while performing banking or other transactions seems to imitate QKD. Is this also a practical example? And if so, how do we rule out the error that can happen over transmitters that are in between the two parties?
These transmissions have their own error correction protocols. For example, it's never the message which is sent. You send more than that, and there are ways of checking whether the message was sent correctly. So that of course has nothing to do with quantum mechanics. This has been around as a method or as an important ingredient for all such cryptographic message exchanges. You have to make sure that the message that has arrived is correct. Okay, let me just give you a very crude way. Let's just say you count the number of ones. I'm saying, just let's say your message is binary, only ones and zeros. You count the number of ones in your message. If that's even, you add a zero to the end of the message. If it's odd, you add a one. That's called a parity check. So once the message is delivered, the receiving system can check whether at least the parity matches. Now that's very crude. You can do much better than that. Much more, you can actually give enough information so that not only can errors be detected, but can be corrected with a very high probability. But all that is standard classical thing, nothing to do with quantum mechanics.
Okay. Okay. So thank you, Dr. Dasgupta, and I just over this to Dr. Kaur.
Thank you, Dr. Halder.
So
Okay, thank you, Dr. Dasgupta. Hello.
Thank you.
Yeah, thanks. Thanks for coming and finding time for us, and then hope we will get you again if we have if we organize something else in some future time.
Okay,
So,
that will be my pleasure. I
yeah,
hope
thanks
you get
for.
enough time anyway. Okay, I will leave now because I have another meeting to go to.
Okay, thank you, Dr. Thank you so much. Okay, so now we'll move on to our second talk. This is the first contributory talk of the day. Okay, this will be given by Dr. Somnath Jalal, Assistant Professor of Physics from Netaji Mahavidyalaya at Arambagh. So Dr. Jalal did his BSc in Physics from Bardhaman Raj College and then his MSc from JNU New Delhi. And then from there itself, he did his PhD in the year 2014. After that, he did a postdoc at IISER Kolkata before joining as an assistant professor at Hooghly Women's College in 2017. And since last December, he moved from there to Netaji Mahavidyalaya, which is very close to our college. So I would like to say thanks to Dr. Jalal for being a contributory speaker today. His topic of the talk is duality between 2D classical Ising model and 1D quantum Ising model, story of topological phase transition. So, Dr. Jalal,
am I audible and visible, Satyakida?
Yes, you are. So, can you please start your presentation?
Okay, thank you for your introduction. And thanks to Aghorekamini Prakashchandra Mahavidyalaya and organizing committee. I hope all of you are doing well, especially in this Corona COVID pandemic situation. Okay, let's start. So, can I switch on my video so that
Yes,
there is?
Yeah, if you want, that's fine.
Okay. Okay, thanks. So let me share my screen and then start presenting. ওকে, স্লাইডটা কি দেখতে পাওয়া যাচ্ছে?
হ্যাঁ হ্যাঁ দেখতে পাওয়া যাচ্ছে, ফুল স্ক্রিন আছে।
Okay, thank you. So good morning everybody. Today I'll talk about some classical and quantum Ising model, which is well and best studied model and theoretical condensed matter physics. So I'll talk about basics on these two these Ising models, and then tell you how they are connected and if the topological phase transition is related to them. Okay, so first let me thank my collaborators, my postdoc supervisor Dr. Siddharth Lal in IISER Kolkata, and Rishabh. He was a BSMS student there and now in Purdue University. And this the whole work is on archive. You can note the archive number and look at the article if you wish. So I have more or less 15 minutes. I'll wrap up. Maximum 20 minutes I'll take. So this is the outline of the talk. I'll not spend time on that. So let me tell you about phase transition. We all have seen these two pictures. The left hand side picture is phase diagram of water. The right hand side is phase diagram of carbon dioxide. It is pressure versus temperature, pressure in the y-axis and temperature in the x-axis. So if you change the temperature keeping pressure fixed, you come across different phases of water. And what is changing? So we can say, okay, the density is changing. So density is called the order parameter. So there is some quantity which quantify the phase, that's called the order parameter. Okay, so let me come back to the to my topic. What is Ising model, or so-called 2D two-dimensional classical Ising model? There are of course 1D classical Ising model and 3D classical Ising model, but my topic is 2D classical Ising model. What is Ising model? So let me remind you of atoms and electrons. So electrons are very important. Whatever we see, the colors, the metal or the magnet, all are happening because of electrons. Because electrons have both charge and spin. The charge degree of freedom is responsible for conductivity, resistance, all those things. And the spin degree of freedom, that is responsible for your magnetism. So in these models, in these theoretical models, of course, they are in real samples. These models works very well. So in this model, we are talking about the spin degree of freedom of the electron. So let's keep this thing first thing first in our mind. So we are talking about the spin degree of freedom, and we are looking at the magnetization. That is the order parameter. Why? Now, when all the spins are up, let's say, or down, let's say, that's called the then the magnetization is maximum, and it's a ferromagnetic state. That's the low temperature state. If I tune the temperature or increase the temperature, the spin will randomly fluctuate between up and down state. So some spin will be up, some spin will be down, and that's the high temperature phase. It's called a paramagnetic phase. So what is changing between these two phases? The magnetization. And what is my tuning parameter? That's the temperature. Okay, so that's the story. For technical detail, the above I have written H. H is the Hamiltonian, minus j by 2, and then summation sigma I sigma j. Sigma I sigma j are the classical numbers only, real numbers. It could be plus 1 or minus 1. Plus 1 means plus up, minus 1 plus 1 means up, and minus 1 means down. So that's the simple physics. So the physics is written in the mathematical form. Okay, so so this interesting problem, it's called 2D classical Ising model, and it's a model for ferromagnetic material. So why something is ferromagnet? We can study this model theoretically and give some answer. So what people do, or what people study? Now they study how the phase transition is happening. So they find out what is the value of the magnetization, or at what critical temperature the ferromagnetic substance becomes paramagnetic. So all spins up to all spins randomly situated. So at some point this happens. That's a critical temperature at some particular temperature. This can be done with real sample experiment, like taking a lump of iron, or you can do some numerical simulations, Monte Carlo simulation, and get some result like this. So there are 4 pictures. T is the temperature. T is 1.0 means low temperature. It's a rescaled T. So that's why I have not given some unit. So T is 1. So 1 means low temperature. So there are lots of dots, means it is most of the spins are up. When at T equals to 4, the 4th box, T is 4 means it is high temperature. So there are lots of white space and there are few of dots. So that means more or less 50% are up, 50% are down randomly. So that's a paramagnetic state. So that's a result from our numerical simulation we did. I mean, I did in my MSc final year course. So these are numerical simulation I have shown you. But these are the formulas. These are the well-known formulas. So what people study? They study magnetization. You can see the magnetization starting from 1, and then at critical temperature it goes to 0. It falls to 0 and then becomes 0 at high temperature. We look at specific heat, we look at susceptibility, and see that at the same critical temperature they are spiked. So those are infinite. So those are becoming infinite. So, and we all know that susceptibility and this thing are second order derivative of the free energy, and that's why it's a second order phase transition or continuous phase transition. So these are classical textbook result. Okay. Now, but there are some issues with this phase transition. Though in textbook this is clearly written that we need a very large sample or very large size to see it. I mean, we mean that the system size should be infinitely large, but in reality no systems are infinitely large. Okay, second point, when we do the simulation or experiment numerically we do it, the system, we cannot take a infinitely large system. So what we take a square lattice, so that's a 2 dimension, and then take periodic boundary condition. You can see the picture. So this is a square lattice. The red dot in the upper row, there is 16, 17, 18, 19, 20. So this is a total number of points, or the spins are 20. The upper side of the 16 is 1. That means the lower side is the nearest neighbor of the 16. Hope the picture is clear. So look at the 20th side. The 20 side, up in the up, the number is 5. That means the first row at the bottom is actually nearest neighbor, or beside the 20th side. So that means we have wrapped the 2-dimensional sheet of spins. So this is the trick to get phase transition point. We will come to this point and elaborate it in topological connection after few slides. Okay, here temperature is a tuning parameter, and one can go from this 2D classical Ising model to quantum Ising model. And before how to go to quantum Ising model, I will tell you what is quantum Ising model. This slide is I have just given the data if somebody asks me how to quantify the phase transition. So these are well-known quantities with critical exponent. The alpha, beta, gamma, these are called critical exponent. You can find it these things in Pathria or Golden Field textbook. Okay, so let me come to quantum Ising model. It's also called transverse field Ising model. And what is the situation here? Now here in the quantum Ising model, there are two terms. One is J sigma I Z sigma. I beg your pardon. This will be sigma I Z and sigma I plus 1 Z. That's the nearest neighbor Z sigma Z interaction. That means spin up interaction. And the second term is H times sum over I sigma I X. So one is sigma Z, and the second term is along sigma X. And I tell you that sigma Z and sigma X, these are Pauli spin matrices. So you remember sigma Z is a 2 by 2 matrix, 1 0 0 minus 1, and sigma X is a 2 by 2 matrix, that is 0 1 1 0. Okay, and why it is a quantum Ising model? Okay, so this is at 0 temperature, And what is a special feature of this thing? Now see, if the second term is 0, then only the first term j sigma I z and sigma I plus 1 z is there. So that means the spin will be along z direction, up up, or that would be down down. Both are degenerate, so both are equally well. So that's called the ferromagnetic state. If my j is 0 and I have only h term, sigma x term, then the spin will be along sigma x direction. There is no temperature. It is only the field, the h term. So the spins will be along x direction. But what is happening here? If I give some small field, small h, then the sigma z will the spin which is along up direction, that will be disturbed due to the term along the x direction. Why? Because those terms do not commute, sigma x and sigma z. The third bracket, you know the commutation relation, this is non-zero. That means that is a quantum fluctuation. So this is not temperature. So temperature is not flipping the spin, but this quantum fluctuation is flipping the spin. So there is also again competition between the ferromagnetic state, where the spin tries to align along up direction, and in the and the h term, which is making the system paramagnetic. So that's the competition between ferro and para, and that's a one-dimensional quantum Ising model. And what is the critical point here? Critical point is j equals to h point. That's the critical point. That's also a very well-known problem. If you study, if you are in master degree, you must study quantum Ising model in 1D. So that's the prototypical model. Now, quantum Ising model is a standard topological model. This picture was described yesterday, so I will not go into it. In the Majorana fermionic language, one can map from spin to fermion and then make it Majorana fermion and then show that this is really topological. Topological, okay, so what does topological means? Topological means edge, the surface and the bulk, they have different properties. That's, as a layman, I understand the topological means bulk state and the edge state, the surface. So if you touch the surface, that will be metallic. If you touch the bulk, the inside the material, that will be insulator. That's the basic principle of topological thing. Okay, now let me come to the spin language. So I am not going to describe the Majorana fermion and all those things detail. I'll talk about in the spin language. So what is the spin language? Now we can find the magnetization, which is sum over all the spins. Now there is a trick, or I'll not tell you. If somebody asks me, then I can give you detail about the first line. So you just remember this is a sum over all the spins. Okay, so there is spin-spin correlation. If I take in the long chain, if I take any two spins, their correlation will change as magnetization, or P, the P square. If I take correlation of the end spin, the first spin and the last spin, and then take average expectation, that will be P to the power 8, magnetization to the power 8. So that's a huge change in the correlation, and that is the effect of topological physics in spin language. Okay, so quantum Ising model is topological. That's a well-studied model, and that is a known model from Kitaev and all those people. I have in the previous slide I gave you the references. Now, if there is a connection between 2D Ising model and 1D Ising model, so then I can, and if 1D Ising model, 1D quantum Ising model is topological, I can say, okay, so there was some topological feature in the 2D classical model also, the 2D classical Ising model also. So let us find out. So this is a celebrated paper by Fradkin and Susskind in 1978, where there is an exact mapping between 2D classical Ising model to 1D quantum Ising model. And how? So the technique is very simple. You just take, so you can see the first column of spin. There are m number of spins, 1, 2, 3, 4 up to m. and all the spins so I write this H2D, the Hamiltonian, as a form like J horizontal, sigma ij and sigma I plus 1j. So that is in the n direction, x direction. And in the y direction, that is a J vertical term, that is sigma I and sigma I comma j and sigma I comma j plus 1. That is in the vertical direction. So one can take all the vertical spin to be a spin vector, that is a sigma I vector, and then write the H2D Hamiltonian. So that is the H sigma I vector and sigma I plus 1 vector, and then again j vertical times sigma I and tau I, because it is the same column and in the same side. So you can do some simple calculation like e to the power of matrix. So find actually the partition function, which is e to the power minus beta h, and then see that this is indeed exact. So this is the exact calculation, and you can see the first the 2D classical Ising model partition function become the partition function with e to the power minus beta h quantumizing. So that's the last line. So I have summarized it. So that is the transformation. The previous slide I have shown the detailed calculation, or you can see the paper if you like. So this is the partition function. So so this is the exact mapping of 2D classical Ising model to quantum Ising model, and how the factors or the quantities, the parameters of the 2D classical model and 1D classical 1D quantum Ising model is. So this is in the red box. H, the paramagnetic term, is 2 into beta e to the power minus beta jh, and j, the ferromagnetic term, is 2 beta h vertical. So j vertical and j horizontal, those are in your j and h terms. Okay, so far so good. So what is the big deal? I have got 2D classical Ising model to 1D quantum Ising model. In fact, Fradkin-Susskind had showed that any D plus one dimensional classical Ising model at finite temperature is actually one lower dimension, that is D dimensional quantum Ising model, quantum model, in fact, not Ising itself or any other quantum model at 0 temperature. That's a very remarkable result. Okay, so what is the topological feature, or what is the big deal? So I have shown you the picture. So Satyagita, do I have 5 minutes?
Yes, you have exactly 5 minutes.
Okay, thank you. So so this is the ground state. All the red things spins are up. That's the ferromagnetic state. One single flip, that means I have given some quantum fluctuation. Now once the spin is flipped, that is down spin, we can flip lots of spin, and then the domain wall is created. So that is the quantum fluctuation which is traveling the whole system, and that is the topological defect, in fact. There are some issues. So what are the issues? So boundary effects are very important, and when we are wrapping the system or making the 2D system cylindrical, or that is wrapping the system, then actually the topological feature is actually coming. So that was our main take home message, that when we on a 2D plane, if we 2D sheet, if we wrap it and make it cylinder, then the topological number is being created. That's the genus 1 feature in the lattice structure itself, not in the momentum space or the Brillouin zone picture. And then domain wall, or this kink in the spin flip process, is actually mimicking the topological feature. And what is in the 2D case then? Now see, when in the 2D lattice, see the below picture, when the temperature is increased, some of the spins are let's say in the leftmost picture, we have the T greater than Tc. That means it's a very high temperature phase. So very few spins are up, many spins are down. Now I lower the temperature, and when I come T equals to Tc, there is a particular domain of spin ups which actually touches the boundary. That's a red dot patch or the region I have given. And then when T is less than Tc, that means very low temperature, the spins are almost all the spins are up. Then I have a big region of domain wall of ferromagnetic chunk. So then it is already in the ferromagnetic state. So this at T is to Tc, I have a boundary touch, if a domain wall which touches the boundary, and that is the topological non-trivial feature which is playing the role in our phase transition in 2D classical Ising model. So that is the take-home message. Please read our archive article if you like to explore our results. And thanks everybody for your presence. So
thank you so much. Yeah. Thank you so much, Somnath. Actually, that's a very nice talk, but I don't want to talk many things because there are many questions. So
yeah, please.
Dr. Haldar, can you just read the questions, or shall I?
You
show
can
up?
ask because
Yeah.
Professor
Yes,
Haldar cannot
Yeah.
short the important question maybe
yes,
because
yes.
there is a next speaker.
Yes, due to time constraint, I just want to mention a few questions from there. So first one is from Anupam Banerjee. So why do you ignore the magnetic field term in Hamiltonian?
Okay, so that is the so he is talking about maybe the classical Ising model. So that is the classical 2D Ising model without any field. Okay,
Yes.
so that is the typical model people studied. So if you give any extra field, that will again so that will anyway orient the spin to align themselves in some other direction. See, in the classical model there is no sigma x or sigma z kind of thing. Those sigma I and sigma j, those are numbers. You can call it ni or nj. So these are only numbers. This is only +1 or -1. So you cannot really give extra field term. That will not be very important. So that is a model studied by Onsager, Kaufman, and Kramers, and all these things.
Okay, so the question from Arijit Mondal is there. What is the significance of the term J in Hamiltonian?
Okay, so J is the spin-spin interaction term. So that is the strength of that's the strength of interaction between two spins.
Okay, and also
hello. May
Yes,
I speak something?
Yes, please go ahead.
Sorry, first of all, I apologize for breaking the protocol. Actually, my
No, no.
question was what is the role of the J? I mean, your transverse field Ising model Hamiltonian was something like J summation over sigma I Z sigma I plus 1 Z plus H sigma I X. I mean, some magnetic field.
Sure.
So, first of all, we neglect the magnetic field term for a moment. Now, for the first term, if I consider a ferromagnetic state, that means all spin are up. Let us take all spin are up. So, if I sum over sigma I z sigma I plus 1 z, that will give you something jn. I mean, if sigma z
Of
are
the
plus
order of that.
minus 1.
Of the order of.
Yes.
Yes.
So that may be the not maybe that is the ground state eigenvalue, I think. So here, how
Yes.
J explain this ferromagnetic state? Why J is important here? What will be for antiferromagnetic state? I mean, what is the role of this J?
Okay.
That I can
Yes.
understand.
So let me answer one by one and very precisely. So here we are talking about this Ising model, and J is the ferromagnetic strength term. So that is a spin-spin interaction term. Here you remember this is sigma I Z and sigma I plus 1 Z. That is along ZZ direction. If you say about anti-ferromagnetic, then I have to talk about Heisenberg model, which is sigma vector sigma I vector and then dot sigma I plus 1 vector. There you have sigma x, and sigma z. or antiferromagnetic also, if J is positive and J is negative, you can say there is this term of see, when J times sigma Z sigma Z, if J is greater than 0, then if the spins are up and the spins are down, both have the same energy because both are +1 into +1 or -1 into -1, since J is greater than 0. So now, so the if J is greater than 0 and one spin is up, one spin is down, then the multiplication is 1 into -1, that means -1. So the Hamiltonian or the energy value is -J. Good. So -J is lower energy, +J is higher energy. So now for a ferromagnetic or for anti-ferromagnetic, I beg your pardon, for anti-ferromagnetic state, the spins will be up and down, so the energy will be lower. So do you get my point?
Yeah.
And
So,
if it is a ferromagnetic, then the correct term should be -J into sigma sigma Z. So then for up or down it will be -J, and anyway the energy would be lower.
yes, but for ferromagnetic state, both the Hamiltonian give the same result, no? Am I right?
Yeah, so the for the ferromagnetic state, one should write -J into summation sigma Z.
Yeah.
And for the so the minus sign is included there. And for the antiferromagnetic Hamiltonian, you should write +J into sigma Z.
Yeah. So,
And
one more
J is
question:
the
can I get independently antiferromagnetic state
from where?
from? I mean,
So the sample decides whether. So if you can calculate the electronic wave function and do the wave function overlap integration, from there the J comes. J, the ferromagnetic state or the hopping term. See, we have learned this 1-year state or block wave function and all those things. So around the nucleus, electron rotates. Now there are two atoms. Electron for a metal, electron can jump from one nucleus to the other nucleus. So there is an overlap integral, right? Because of the overlap integral, electron can jump from one side to the other side. That's the metal. If the overlap is very large, that's the metal. If the overlap is very small, that's the insulator. Did you get my point?
yeah.
So there the overlap integral actually decides whether the sample would be ferromagnetic or antiferromagnetic. We don't have any choice.
No. My point is like that. For suppose for ferromagnetic state K 0, that is a ferromagnetic state. That is an eigenstate of Heisenberg Hamiltonian.
Yeah.
But if I consider the state 0, 1, 0, 1, 0, 1, but that should not be an that independently should not be an eigenstate of the Hamiltonian. That may be some superposition of some other terms.
Exactly. Superposition of all those excited states actually.
Yeah.
All
Okay.
the spin flipped excited states. Spin flip means excitation.
Okay.
0, 1, 0, 1 means that's a superposition of all the excited states. Thank you. Any other quick question?
Yes, from Supriya Ghosh, what is the significance of quantumizing model?
Yeah, so quantumizing model tells you that without any temperature, quantum fluctuation shows you phase transition. So the H term in the quantumizing model, which is along sigma x direction, that is induces quantum fluctuation that is equivalent to temperature. And actually this is the connection between classicalizing model to the quantumizing model, which Fradkin in 1978 figured out. Did it answer the question?
Okay. So what is L here? Another question is there. Capital.
L was so for a finite chain, the L is the number of spins I have taken or we can take. The 1, 2, 3 up to L. L could be 100. So there are 100 spins sitting on a chain, right? So actually for a nanowire or a sample, we take actually finite size, right? So this is a micrometer size or nanometer size thing. So there are finite number of atoms for the experimentalist to do some experiment on topological features or these Ising-like features. So from that thing, whenever we do numerical things, we take some finite size lattice or finite size crystal to check the experimental results. So L is the number of spins.
So, last or participant, that Arijit Mandal, has asked another question, that can I define spin glass state using these order parameters?
Yeah, so spin glass, which I myself asked yesterday. See, paramagnetic phase is different from the spin glass state. So that's a very important point. When we quickly jump from ferromagnet to paramagnet, there is maybe some cooling process. If I rapidly cool something, then some sample become glass. So that's a glassy situation. Maybe Shatyagita can explain the glassy phase more clearly than myself. On a two-dimensional thing, when two-dimensional Heisenberg model, if somebody knows what about Heisenberg model, so there is called resonating valence bond, or for antiferromagnetic sample, spins try to align up and down. Now you can consider so up and down, nearest neighbor one spin up and the next spin is down. That's the low energy state, ground state. Now you can consider triangular lattice. There, all the spin up down is not possible. You can consider ABC. Suppose A and B are up down, and if C is up, then AC is both up. So there is frustration comes. That's called spin frustration. The system is frustrated because all the spins are not up down. Then the glassy phase comes actually. So see, when you from water to ice, if you cool very fast, there is a gel kind or glassy type phase in water also. So those glassy phase, so the spins are frozen in some highly, you can say, metastable state with very particular lifetime maybe. So those phases, glassy phase or glassy state, it looks like paramagnetic, but it is not. It is not. So there is some other order parameter like antiferromagnetic magnetization, but it is antiferromagnetic magnetization kind of thing, which can distinguish your paramagnetic glassy state. That should be the order parameter. Antiferromagnetic antiferromagnetic magnetization.
Okay, so last one from our colleague Surajit has made a question. Surajit Min, this theoretical Ising model perfectly matches with experimental result.
Yes, yes. So there are lots of material from I don't exactly remember. So there are lots of material which are which obeys the simple ferromagnetic Ising model, both 2D classical Ising model and also 1D quantum Ising model. Please Google it, or I can you can ask me through my email or my phone number. I'll give you lots of sample names.
Okay, there is also another question from our student actually,
Yes, please.
He just asked.
Students are welcome.
Yeah, that's what it is. So he says that what is the application of topology that we can think of?
See, so maybe yesterday's speakers, they were the correct or candidate to ask this question. See, topological. So why people are running after this topology? So what is the big deal? See, you can see a surprising sample where the sample, it is not a copper or iron. Some samples where the boundary is actually metallic, inside it is insulator. Is not it a great sample? So it is experimentally people are trying to find out, and there are lots of application, because you can see yesterday also we have seen this 2D, two-dimensional electron gas, 2DEG, and then we saw the spin current. So when we say the current is flowing, the electrons are flowing in the wire, we don't worry about whether the up spin is moving or the down spin is moving, right? We see the electrons are moving. Now they are actually, they can get the spin dependent current, spinotronics application. There are lots of spinotronic applications. So you can freeze, or you can ask the up spin to move, or you can ask the down spin to move with great correlation length. I mean, with a great correlation or control. So you can really see the, okay, the up spin is moving. You can see it, or you can see the, okay, the down spin is only moving. Okay, so there is lots of spinotronic application, and in this quantum computation, which Professor Ananda Dasgupta just said, to make quantum computers or to make high TC superconductor, these topological insulators or topological physics, they are playing big role actually.
Okay, so there is another.
this answer.
Yeah, so that
Thank
was.
you, Dr. Jalan, and over to Dr. Satyaki Kaur.
So there is another question from Sanjukta Pal.
Oh, Sanjukta, yes.
Yeah.
Please.
So yeah, so okay, let me just read it out. So
Okay, okay.
she said that you also have a temperature of for determining the critical temperature in your quantumizing model, other than the magnetic field. As temperature is
no, I don't have a temperature. So
no, she's saying that
okay.
you
you also
so
have a
that
temperature for determining.
as temperature is not a fluctuation here, does it just choose the probability in Monte Carlo simulation?
Just to the okay. So first of all, there are lots of things. Maybe so the fault should be speakers. So I have not maybe I conveyed the message clearly. See, the classical IDC model is temperature dependent. Things are happening where in the classical IDC model, the spins are up or down, that is +1 or -1. I am doing the Monte Carlo simulation and flipping the spins. So when I flip my spin, there is a temperature scenario. So there is lots of story. How should I flip the spin? Should I flip the spin or not? Lots of things, blah blah blah. So those are the Monte Carlo simulation for the classical spin system. For the quantum spin system, I don't have any temperature. It is only the quantum fluctuation which is flipping the spin. It is a quantumizing model which is only J and H terms are there. It is a ferromagnetic term and the transverse field term, that is along X direction. There is no temperature. Please remember there is no temperature. Now there is a connection between 2D classical to 1D quantum, and there I have so that theoretical connection, that's the mapping. There I have there we have, or Fradkin has identified what is the J term, what is the ferromagnetic term related to the classical thing, and what is this transverse term related to the classical IC model. So quantumizing model, we are doing at 0 temperature quantum IC model. Now she can ask, okay, can quantumizing model, if I put temperature on the quantum IC model, what will happen? It will kill the quantum effect. So the classical feature will come, and all the spins will be randomly oriented along up down, because remember KBT. So that's a very nice question. KBT, actually KB, Boltzmann constant into temperature, your room temperature, that is very much greater than your J or H. So the value of J or H in joule is very less than the KBT order. Okay, so temperature will kill the quantum effect. That's why people in lab, they are so that is a low temperature lab. There people are working in 2 Kelvin or 4 Kelvin, 20 Kelvin order. There you can see the quantum effect. You can see quantum effect in 2 regions: low temperature and very tiny length scale of the order of angstrom or nanometer. There you can see quantum effect, or at very low temperature like 10 to 20 Kelvin, 0 to 10 Kelvin maybe.
Okay, thank you so much.
Thanks for your interest. Yeah.
Sir, does 2 Kelvin is reachable?
Yes. So in the audience, is anybody is from an experimental quantum matter physics? So I believe 2 Kelvin is reachable in Bardon University or in IISER Kolkata for sure.
No, I am from ISCS, and there is, I think, 3 Kelvin, up to 3 Kelvin reachable lab.
So what is the superfluid temperature? It's helium
2.4
temperature?
2.4 Kelvin, right?
Yeah.
So you have reached 3 Kelvin. Okay, you try hard and you will get 1 Kelvin more. I mean, one can be less actually. You have reached 3 Kelvin. Anupam.
No, I heard about that in labs.
Yes, yes. So that is reachable.
Oh, okay,
Reachable.
okay.
It is reachable. You talk to your colleagues or friends
Okay.
over there. You are from which institute?
I am from Indian Association for the Cultivation of Science.
ISCS.
So
Jalapur,
are you in theoretical department or?
No, I am a BSMA student, third year BSMA student.
I see. Okay.
So Satyagita was from that institute.
Yeah, I had a postdoc there long time back.
Okay. So thank you for your interest. So I am sorry that I took some time from the next speaker.
Yeah, but that was a nice interacting question answer session. But and also I'm sorry that because we are running not according to our schedule. But thanks again, Somnath. That's for a nice, interesting talk. And then maybe we'll just move on to our next
Thanks to the audience. Yeah, stay safe.
Okay, so I'll just move on to our next talk. Our next speaker is, that's another contributory talk to be given by Dr. Amit De. Dr. Amit De is an assistant professor of physics from Ramananda College, Bankura. He did his BSc from St. Paul's Cathedral Mission College and MSc from University of Calcutta. And then after that, he did his PhD from Shah Institute of Nuclear Physics. And thereafter, he moved to Ben Gurion University in Israel for his first postdoc. And then his second postdoc was from ICTS Bangalore. And last year, he just joined this Ramananda College as an assistant professor. So we thank Dr. De for being a contributory speaker in our webinar. And the title of his talk is Cavity QED based stimulated Raman adiabatic passage. So the name sounds tough, but I'm sure Dr. De can help us on that. So Dr. De, welcome. Please take charge of the session and start your presentation.
Thanks for the introduction, Satyagita. Am I audible?
Yeah, you're audible.
Yeah, so first I would like to thank the organizers for giving me this nice opportunity. And I wish all good health during this pandemic time. So I start by sharing my screen. Let me switch off the video. So is it visible?
Yes, it's visible.
Okay, so I'll be talking about a few aspects of cavity QED physics. So basically its application in stimulated Raman adiabatic passage. So this work is done in collaboration with Manas Kulkarni and ICTS Theatre. So I start by recapitulating a few fundamental concepts. For example, so this adiabatic theorem tells us that if a perturbation applies sufficiently slowly on the system always finds this state in its instantaneous eigenstates. So this perturbation could be a time-varying Hamiltonian. So this statement basically separates out two time scales, one associated with the variation of Hamiltonian, and another one is the characteristic time scale of the system. So for example, if we take an infinite well and a particle inside, so this panel A is basically the ground state of the particle when the width of the well is A. So let's say we are changing the width of this well and we are making 2A, just doubling the width. So if this process is performed sufficiently slowly, so you can see in panel B that the wave function adapts the instantaneous eigenstate of this new configuration. So this is the adiabatic evolution. And if it's this process is done all on a sudden, the wave function remains as it was initially in panel C. So clearly, this wave function is not eigenstate of this new configuration. So C is sudden and B is adiabatic evolution. Now, there are certain class of systems which are very sensitive to its initial conditions. So if you make slightest of initial error in initializing the system, so the future outcome could be drastically different. So there is always, it's always hard to make predictions on these systems. For example, the weather and stock markets and traffic movements, these are the example of chaotic systems. So basically what happens, let's consider an 1D problem. So let's choose two copies of a same system, and their initial condition differ by delta x naught. So it's infinitesimally small. They are too close to each other. So what happens for chaotic system is uh, the difference between these two trajectories that exponentially diverge. So the behavior is exponential lambda t, and lambda is called Lyapunov exponent. So this basically measures the rapidity of chaos, or the rapidity of divergence of these two trajectories. Excuse me. So you can imagine, even if you start with a small error, that can result into a quite different outcome. Okay, so Edward Lorenz has a quote there: when the present determines the future, but the approximate present doesn't approximately determine the future. So if you make a small error, that could result a very different outcome. So now what happens when we consider a chaotic system and it's also going through a adiabatic evolution? So there are two timescales involved. One is the adiabatic evolution timescale, and another one is 1 by lambda, which is the chaotic timescale, or the divergence which measures the divergence of classical trajectories. So I'll touch this issue and show some interesting results. So to explain the physics, I take the platform of cavity QEDs. So cavity QED is basically comprised of quantized light, which is confined within this cavity. In addition, there is this two-level system, or a qubit, which is coupled to this cavity modes, that is the photons, via this Jaynes-Cummins-like interaction. So G is the strength of interaction, and A is the destruction operator for the photon, and S plus is the raising operator for the qubit, or this two-level system. So this is basically this basically deals with a light matter interaction. So you can see this kind of interaction is energy conserving. So basically you raise this particle or this atom to excited level in expense of destruction or absorption of one photon. So this is the basic Hamiltonian that describes cavity QED systems. So now this cavity QED systems have diverse applications. For example, it can be used in quantum networks, in communicating distant qubits, and it's also used in quantum information processing and quantum simulator. And these systems have remarkable controllability and tunability, and it's also scalable. That means one can design bigger systems using this cavity QED components. And the fabrication techniques are also well developed. So you can see an array of, or a lattice of 72 cavities has already been experimentally realized. And various lattice geometries, lattice with complex geometries like Kagome lattice, this has also been designed using cavity QEDs. So here each unit is a circuit QED. And similar concept applies to a slightly different system, which is optomechanical system. So here basically the cavity photons that interacts with a mechanical mode via radiation pressure. So these kinds of applications are there. for light matter interaction, and various phases also have been realized using cavity QED systems. For example, self-trapping or localization, delocalization of photons, etc. So now let's look at the basic structure of energy levels of Jaynes-Cummins model. So this is the model. This is the light matter interaction. In addition, there is a photon and this qubit. So what happens if you start with two photons in the system? So there is this oscillation, out of phase oscillation between the photon content and the qubit. So basically, two photon content that gives one photon to the qubit degrees of freedom that goes from minus 0.5 to plus 0.5 and again comes down by releasing the photon. So this kind of oscillation is called Rabi oscillation, and the time period of this oscillation depends on square root of n, which is the number of excitation present in the system. So now let's look at the spectrum. So when there is no coupling, that is G is 0, so this is uncoupled structure. So atom has two levels, one ground, one excited level, and photon states are just like the eigen energies of linear harmonic oscillator. So energy levels are equispaced. Now, if we switch on G, the light matter coupling, so basically these levels, these photon levels, they get raised and split up. So there is a square root of n dependence of this energy gapping. So it's no more linear. It's not E is equals to NH cut omega. This scales with the square root of n. So this is the clear signature of anharmonicity or the nonlinearity present in the system. So now let's look at this protocol, stimulated Raman adiabatic passage, or STIRAP. So this kind of protocol is well used in atomic and molecular physics, in waveguide optics, in state transfer and state preparation in quantum information processing. So basically, if you look at the schematic at the left hand side, so there are three energy levels, 1, 2, and 3, or it could be a physical sites. So initially, let's consider there are atomic population or n number of particles at site 1 or in state 1. So our job or our target is to transfer this particle completely to energy level 3 without populating level 2. So the reason we want this, because this state 2 is in general decaying state. So basically, due to spontaneous emission, the particles, if the particles goes here, that can fall back to either of these states, 1 or 3, because of spontaneous emission, and we don't want that. We want 100% transfer from 1 to 3. So this can be achieved via following this exotic state, which is called dark state. So this dark state is basically one of the eigenstates of this system. And so you can see, so this dark state doesn't project onto state 2. So it's only a superposition of state 1 and state 3. So this protocol is processed via this counterintuitive pulse sequence. So omega S and omega P are basically the coupling between 3 and 2 and 1 and 2. So why we call it counterintuitive? We have population at site 1 initially, but first we switch on the coupling between 3 and 2 via this omega S coupling. So it gradually grows to a maximum value and start falling. Then the coupling between state 1 and 2 is switched on, which is the pump pulse omega P. So that's why it's called counterintuitive. And at the end of this pulse sequence, we find that all the populations, or nearly all the populations at site 1, that gets transferred to site 3. So you can see the coefficient cos theta and sin theta. So basically, going through this whole pulse sequence is basically changing this theta value from 0 to pi by 2. So if you put 0 in this dark state, so last term goes off, so it's 1 basically. So initially it's 1, and finally if you put pi by 2 here, so first term goes off and it's 3 basically. So dark state rotates from 1 to 3 via this pulse sequence. And you can look at the population dynamics here in the lower figure. So we start with n number of photons, or 1 at site 1, and it goes to 0 as these pulses are switched on and this process is completed. And site 3, which starts at 0, it gets all of its population, and site 2 is negligibly populated. So this kind of coupling is written in as this Hamiltonian omega p a1 dagger a2 plus Hermitian conjugate and omega s a2 dagger a3. So basically, in this picture, there is no nonlinear interaction. So nonlinear interactions are like atom-atom interaction or photon-photon interaction. So these kinds of nonlinear interactions are absent here. So this is called linear stirrup. And we see there is an existence of this dark state. Now we ask the question whether, if there is certain nonlinearity in the system, like the light matter interaction or the JC Hamiltonian, can we have similar dark state? Or is it possible to transfer photonic population from cavity A to cavity 3 by negligibly populating cavity B? So here is the diagram. So J1, J2 are the coupling between cavity A and cavity B and cavity B and cavity C. So for simplicity, we put nonlinearity or the light matter interaction only in cavity 3 or cavity C. So here is our Hamiltonian. So ABC are 3 cavities, and JC stands for James-Cummins interaction. And here is coupling. So J1, J2, these have the Gaussian form, and tau is the width of the pulse, width of the Gaussian pulse. So 1 by tau measures the rate of sweeping these pulses. So you can imagine if tau is larger, 1 by tau is small, that is sweep rate is small. So the evolution is slow. And if you look at the form of J1 and J2, it basically depends on this parameter T tilde is equal to P by tau. So there is no appearance of tau as an explicit variable in this Hamiltonian. So we basically parameterize the Hamiltonian in terms of T tilde. Now let's look at some results. So here we calculate the stationary points of this Hamiltonian. So the stationary points are only functions of T tilde, basically the parametric time, and it has no dependence on the rate. So it only depends on, so you can basically choose various tau, various sweep rates, but T by tau, that ratio remains same. So it's basically the Hamiltonian is, because the Hamiltonian is parameterized in terms of T tilde. So now let's look at how the stationary point solutions looks like. So let me zoom this figure. So these gray lines are the stationary point solution. So you can see there is one branch of stationary point solution that starts at 20, because we took 20 photons to begin with. So that starts at 20 and ends at 0 for the population at cavity A. And correspondingly, in cavity C, that begins at 0, that's close to, ends close to 20. So there exists a dark state like state. It's not exactly dark state because it's not reaching 20, but it's almost a dark state. That's why we call it dark state like. So our job is to follow this particular line, particular branch of stationary point. So that leads to a complete transfer of population from cavity A to cavity C. By the way, the stationary point solutions are analogous to finding eigenstates in quantum Hamiltonian. So these are basically semi-classical treatments. So now let's look at the dynamics. So this stationary points has nothing to do with the rate of sweep 1 by tau. Now let's look at real-time dynamics. So we choose two examples. One is fast dynamics, that is the red circles, and another one is slow dynamics, that is the blue dots. So by fast dynamics, I mean 1 by tau is greater, that is the pulse width is smaller. So so you can see, and another point is that by Lyapunov exponent analysis, we find that within this parameter window marked by this dashed line, so here the system becomes chaotic within this window, and on either side of this window, system is non-chaotic. So you can see, before reaching this chaotic window, the slower dynamics following the stationary point solutions in a better way compared to the faster dynamics, the red circles. So which is the standard statement of adiabatic theorem. So slowness is always better, or slow evolution is always better for adiabatic following or getting the instantaneous eigenstate. But as soon as
Amit, sorry.
yeah.
Can you wind up in 5 minutes?
Yeah, I'll try.
Okay. Thank you.
Okay. So as soon as the system enters the chaotic window, it behaves in an opposite way. So here within the chaotic window, the red circles or the fast dynamics is more or less following the stationary point solutions, whereas the slow dynamics is getting killed. So it's the reverse situation. So in a non-chaotic situation, the slower is better, and within the chaotic regime, slower is actually worse. So this tells us that too much slowness is a killer when chaos emerges in the system. So this happens because, to begin with, we have some initialization error. It could be a numerical error or experimental error. So that's not getting magnified when we are in a non-chaotic region. But as soon as we enter the chaotic region, that initial error that's getting magnified, because chaos has this property that it's hypersensitive to its initial conditions. So the longer the system spends within this chaotic window, so it gets killed, more it gets killed, and we are detached from the stationary point we are following. So what happens is, for non-chaotic regime, slower is better, and for chaotic regime, slower is worse. So here I state the adiabatic theorem again, and we find that the slower is behavior for chaotic situation is actually contradicting the standard adiabaticity protocol. And this behavior is not limited to this cavity QED systems. It's a general behavior which can be found in ultra cold systems also. So now this final result. So here I plot the efficiency of a stirrup versus the sweep rate. So the transfer efficiency is defined as NC at infinity by N. NC is basically at the end of the number of particles or the number of photons deposited in cavity C after completion of stirrup pulse, and capital N is the number of photons we begin with, basically the number of photons in cavity A initially. So if it's greater than 95%, we call stirrup an efficient process. So now let's compare the linear and non-linear stirrup. So basically, when the system is linear, that is, we put light matter interaction 0. So you can see after, so basically x-axis, if you in x-axis, if you go left, the sweep rate is smaller. That is, the evolution is slower. So beyond a limit, the efficiency is always unity, irrespective of how slow you go. Okay, so slowness is always better when GC is 0 or there is no light matter interaction. Now, if we switch on the light matter interaction GC, which is 0.1 here, we see the efficient region that is squeezed here, that is limited by this red boundary. So within this efficient region, efficiency is greater than 95%. But if our the rapidity of our evolution, the slowness goes beyond this red line or the lower bound, that becomes chaos dominated, and efficiency falls below 95%. So this chaos basically limits the efficient region. And if we keep increasing this GC value or the light matter interaction, the efficient region is shrinked. You can compare B, C, and D. So for very high value of GC, so it's very limited efficient region, and one can imagine for some greater value of GC, there will be no efficient region and no adiabatic process or transfer process is possible. So the strategy to overcome the detrimental effects of this chaotic breakdown is to choose your sweep rate or the rapidity of your evolution somewhere within this efficient region, so that you get a good transfer. So I conclude. So this TDUP is an excellent process that dynamically explores chaotic and non-chaotic phases. So this work is published in this paper. So this is an open access journal, so one can access it anywhere. And we have shown that counterintuitive slower is worse behavior is reflected when there is chaos, and optimal design of pulse parameters that guarantees the efficient transfer of population from cavity A to cavity C. And these kinds of analysis is very useful because cavity QED is well used in state preparation and state transfer in quantum networks. And here we mainly considered a closed system, that is, the number of photons is conserved here. So it would be interesting to study driven dissipative format of this problem. So thanks for your attention.
Thank you so much, Dr. De. That was a nice presentation. And also, I must say that's also very lots of work. And then you also showed that there are some future directions also you want to work on that. So there are some questions. Let me just go over that first. Saurabh, shall I just do it or? Yes.
Yes, we can ask a few questions from here.
Oh.
Due to time constraint, we are running out of time. Very short questions are there. So we can have a question from Arijit Mondal. So in okay, so first from Anupam Banerjee, does this coupling correspond to time-dependent perturbation theory?
Does this coupling correspond to, yeah, this, which coupling you were talking about?
Anupam, are you here?
I think the G thing that you mentioned, is that what you, in your Hamilton there's a term
yes,
G,
sir, yes,
right?
sir.
G?
Small G.
No,
there's a,
no. G has nothing to do perturbation theory here. Here the perturbation is.
I mean the dark state. You said something about the dark state. I didn't remember properly in your slide.
So can you still see my slides?
Ha.
So which one? So
Yeah,
dark state is basically this state. The superposition
yes,
of state.
yes, sir. In this.
Yeah, no. Here it has nothing to do with perturbation. It's an exact solution. So you take this Hamiltonian and diagonalize it. So you get the eigenstates, and dark state is one of them. And we call it dark because this prohibits any spontaneous emission from state 2, because it has no state 2 here. If you take inner product with state 2, it gives 0. So if there is no spontaneous emission, there is no emission of photons. So that's why it's dark.
Okay, sir. Okay, sir.
So following to that, I have one question to Amit. So you,
Yeah.
are you getting that? Is it like you are doing this diagonalization with containing these 3 states, and then
Yeah.
from there you are getting some eigenstate which is like that?
Yeah. One of the, you will get 3 eigenstates. Let's say we have 3 sides. So out of those 3 eigenstates, you have one eigenstate, which is a dark state, which is this.
I see. Okay.
Okay, so Dr. Jalal has okay, from Arijit Mondal. The question is, in optomechanical system, is the mechanical mode always vibrates because of radiation pressure or some external force is applied?
The mechanical mode is said to vibrate because of the radiation pressure.
Okay.
Yeah, that's what is pushing it.
Okay, thank you. So Dr. Jalal has made a query. So his first question is, on a lattice of cavities, where is photon hopping term T a to the power dagger A term? That means, where
On a
is photon hopping
lattice,
term? The question is, where is photon hopping term?
lattice
So may I
cavities, where
clarify?
is? Yeah, sure.
May I clarify? Hi, Amit.
Yeah, sure.
So thanks for the nice talk.
Hi.
So what I meant
Hi.
in that question is, on a lattice, so there are lots of cavities are there, right? So they are array
Yeah.
of the cavities. So
Yeah.
the light should hop from one cavity to other. So there should be some T A dagger A. I mean, photon hopping
Yeah,
term.
it's there basically. It's A
Okay,
dagger
okay.
B. So A and B are basically photon
see.
operators in cavity A and cavity B.
I see. Thank you. And the second question was, in this James Cumming model or this Rabi model, we took the dipole interaction term, right? P dot E, and P is like Sx or sigma x, and electric field is A dagger plus A.
Exactly.
And we do the rotating wave approximation. I mean, we drop the first rotating terms or the energy non-conserving, and we took S plus and A. What you showed actually, maybe in your slide, S plus in the first slide, or So these are James Cumming.
Yeah.
But if you keep the full dipole interaction term, you see my point. Whole light mass interaction term, that is Sx times A dagger plus A. So have you done it, or maybe that may be your future direction, or is there any known result which I missed maybe?
That I have not tried, but I mean, I did some simulation on that. So we found that it basically heats up the system because it's not energy conserving. There will be A dagger S plus term. So in optomechanics, there is a nice analysis for these terms. They call it heating effect. So basically that heats up the system. So you can look for this review articles for optomechanical systems. So there you will find this kind of analysis.
Okay, thank you.
Okay, so Dr. Dey, can you, Sanjuta Pal has asked a question that, can you point out how A2 acts on Kate1 or Kate3 as the cosine or sine functions did not have Kate2 attached with them? How does A2 actually help in the whole population process?
So you are saying why there is no A2 here? Sorry, I didn't get the question.
I think
Sanjuta, yeah.
Can you please decode?
That was Bra. Yes.
So how A2 acts on, so when A2 acts on Kate 1 or 3, that gives 0. as cosine and sine functions didn't have attached to them, how A2 actually help in the whole population. Probably the question is, I mean, so there is no connection between state 1 and 3. So then how is it
Yes,
transferring from
she is
1 to
asking
3?
that why is bra2 not present? That is the question.
So that is the goal of this protocol. As I said, I mean, 2 is in general decaying state. So we don't want the atomic or photonic population to go there. Otherwise, there is a certain probability that the photons will fall back to either of this state, and the transfer process won't be smooth. And that can be obtained or achieved by this following this dark state. And probably that answers her question, or
Actually, yeah, thing on that is what I'm just thinking. So you have this omega p and omega s. These are the two hopping amplitudes, right? For
yeah,
going from 1 to 2 and then 2 to 3. So
yeah,
then maybe the question what she's asking is that, means what is how you get this state, like means how this 1 and 3 is connected, like physically how we can
yeah, yeah, yeah.
see that.
I understand. Yeah. So basically, what happens? It's basically uh, quantum mechanical superposition. So when you first switch on the coupling between 2 and 3, so there is a superposition. A state is prepared, which is a superposition of 2 and 3. Then you switch on 1 and 3. So we get a superposition of 1 and 2. So basically, these two states, these two superposed state, they destructively interfere, and the probability amplitude of getting population at site 1, that basically gets cancelled out. So the ultimate result is this dark state.
Okay, that is interesting.
So this is
Okay.
basically quantum interference effect.
Mhm.
Yes, so over to Dr. Kaur, as there is no more query. Thank you, Dr. Day, and
Thank
let's
you.
proceed for the next talk. Yes.
Oh
Thank
yeah,
you.
yeah, I forgot. Yeah, Sangyukta was in the
Okay.
same group as Amit.
Yeah.
Okay.
Yes.
Yeah. Okay. So thank you so much, Dr. Day. That was a nice talk, and there's a nice
Thanks.
interacting question answer sessions. So we'll now move on to our next speaker. So now we have two short presentations left. So the first short presentation will be given by Mr. Rajdeep Banerjee, who is a final year student, final year BSc Physics honor student from our college. He's a local guy from Kamarpukur, and he's a good student in our department. So this is just his first naive attempt. So hope you will all like it. So the title of his talk is Quantum Tunneling, a World of Possibilities. So Rajdeep, I'll request you to kindly start your presentations. You are here, right?
Yes, sir.
Okay, so you can start your presentation.
Yes, sir. Thank you so much for giving me a chance to discuss my topic. Let me share my screen. Sir, is it coming?
Yeah,
Hello?
it came, but make it full screen.
Yes, sir. Okay. So, welcome everyone. I am Rajdeep Banerjee, a student of AKBC Mahavidyalaya, Department of Physics. Now, into this, my topic is what is the quantum tunneling in our quantum mechanics. Now, this is going to be a very short presentation on a very interesting topic of quantum mechanics. Now, before getting into the topic, we should know that why we will learn quantum tunneling. To know the reason, we have to go back to the history behind it. Now, the idea first arises when we came to know about the matter wave of particle. According to de Broglie, a moving particle should associate a wave. And the consequences of that wave nature of particle helps us to change a lot in our quantum mechanical world. On the other hand, it was impossible to explain the alpha decay process in nuclear physics with the help of the classical mechanics. So it pushes us to go to the quantum mechanical explanation. Then the process was experimentally shown by Leona Esaki in 1958 through his tunnel diode. Now, what is quantum tunneling? As you all know that in quantum mechanical world, particle behaves like wave or wave packet. So the particles have wave-like nature here. Now, classically, if a particle hits a barrier with an energy less than the height of the barrier, then the particle can never cross the barrier. But in quantum mechanics, as we treat the particles as a wave, so there will be a certain probability for the particle or the wave to be found inside, even at the other side of the barrier. Now, this process is known as quantum tunneling. Now, how this can be? To examine the process, we divide the whole system into three parts or in three regions. In region 1, the wave incident on the barrier. And the Schrodinger wave solution for region 1 will be somehow like in this a to the power ikx plus b to the power minus ikx. In region 2, the Schrodinger wave solution is c to the power alpha x and d to the power minus alpha x, or you can say it c to the power kx plus d to the power minus kx. Now this is an exponentially decaying solution. Now if any portion of the wave function is to be found inside or at the outside of the barrier, which is in region 3, then we can say quantum tunneling occurs. Now, the width of the barrier is the most dominant thing here for determining the transmission probability. Now, we can explain the alpha decay process easily with the help of this quantum tunneling. But before doing that, we will see that why we cannot explain the process with the help of classical mechanics. If we see the process of alpha decay from a heavier nuclei, we will see that it has a maximum kinetic energy. The alpha particle that emerge out from the nucleus has a maximum kinetic energy of 4 to 5 mega electron volt. But when we see the potential curve of nucleus, we can see that there is a potential barrier of maximum height at 25 to 26 mega electron volt. Then how the alpha particle with that lower kinetic energy can escape from the nucleus? Classically, this was impossible to explain. But if we apply quantum tunneling, we can say that there is a certain probability, there is a certain transmission probability for the alpha particle to be found outside of the nucleus. Now, George Gamos first explained the alpha decay with uranium-238 using this tunneling method. One of the most successful application of quantum tunneling nowadays is scanning tunneling microscope. Now, this is basically the structure of a scanning tunneling microscope. When this metal tip, usually made of tungsten or platinum iridium, is brought too much closer to the sample, such that the electron from the tip can tunnel through, across the gap and create a current into the tip. As the current is too much low, we can use a tunneling current amplifier to amplify the current. As the distance between the tip and the sample increases or decreases, the current will decrease and increase respectively. So using this current, we can easily draw the atomic structure of the sample. For example, we can have a structure something like that. Another most useful application of quantum tunneling is are tunneling diodes. This is nothing but highly doped p-n junction diode, as we all know that. When the p state and n state are properly aligned, which is at low voltage, it allows the electrons to tunnel through the barrier. But as the voltage increases, the p state and n state becomes to be misaligned, and then the tunneling of electrons becomes very much low. As a result, at this situation, as the voltage increases, the current will decrease. And this region, this is a very useful region of this diode, and known as the negative resistance region. Why it is so useful? This is so useful because of that. In this region, the diode can operate at a very high frequency, which may be in gigahertz range. Another application of quantum tunneling is the force sensors. Now, the force sensors are usually made of quantum tunneling composites, which you also say QTC. These are usually made of insulators. When it is flexed by an applied force, such that the atom of QTC are brought close enough so that tunneling can occur. This tunneling process changes the insulator into a conductor with a significant and exponential decay in resistance. There are also some future possibilities for this application of this process. These are the quantum computers. Now, the quantum, as you all know, that the quantum computers are too much powerful than our current generation computer. Just for a comparison, we can say that a 40 qubit quantum computer is equal powerful to a supercomputer nowadays. Now, Google, IBM, Intel microprocessor are investing a lot in quantum computers and the development for it. Our Indian government has also developed the quantum information and science and technology for developing those quantum computers. That's all. Thank you.
Thank you so much, Rajiv. That was a nice presentation. So if anybody has question, you can directly ask. Let me actually see whether I can.
I can see there is a question from Anupam that he says that I think C is 0 for region 3 as it is exponentially decaying. Can you check, Rajdeep?
Yes, so when we solve the Schrodinger equation, we will get that the C is 0. But just for example, I have put the equation in that. It is a general equation. But when you solve it, we can get that C is 0 as there is no reflection in the region 2.
Okay. Thank you, Rajdeep, and Satyagita. Can you take this session? Okay. Okay. So, Satyagita, are you there?
Oh, sorry. I forgot to turn it on.
Okay.
Yeah. Actually, there is some problem with feedback form, so I was actually trying to figure that out. Okay, but let me just go ahead with the next talk. So we have one last talk left for today's webinar. So that's a short presentation to be given by Dr. Shampa Mondal. She's an assistant professor of our college, AKPC Mahavidyalaya. Dr. Mondal did her BSc from Bardhaman Raj College and MSc in physics from Bardhaman University. And in 2003, she got her PhD degree from also from Bardhaman University. In the meantime, she joined in 2008 to our college as an assistant professor, and since then she is serving our college as a loyal faculty. So the title of our presentation today is Future of Energy Storage System. So Dr. Mondal, you can take over the session and deliver your talk.
Thank you, Satyagita. I got PhD in 2013, not 2003.
Did I say 2003? I'm very sorry. I'm very sorry.
Okay, thank you. Now let's get the presentation here. Is it visible, Satyagita?
Yes, it's visible.
Okay. Yesterday and Today there is lots of theoretical quantum mechanics. My topics is just different. There is some experimental works on some energy storage systems. So let's start. What is the future of energy storage systems? So my outline of this works is why storage system is essential. There is some advantages and disadvantages of batteries. Comparison between battery and supercapacitor. Character of a good supercapacitor material. Current research on these topics, and what are the facilities available. So before I going to my topic, why the storage system is essential. We all know that for our climate changing or global warming system, we are going to from non-renewable to renewable energy systems. But these all renewable energy systems are incomplete without efficient storage systems. In recent times, we use electrochemical storage systems to store energy of renewable systems. There is some climate benefits of this renewable energy storage system. So now we are mainly use lithium ion batteries and some lithium originated batteries and supercapacitors. There is mainly my research works. My paper is only on supercapacitors. So before I go into my research area, what is the configuration of this lithium ion battery? We have already used this lithium ion battery. Mainly, we are trying to continuous miniaturize of these portable electronic devices. There is cell phones, digital cameras, notebook computers, etc., in which these types of lithium ionized batteries are emerging as one of the most promising nanotechnology for this energy storage system. This technology is mainly applied to green transportation systems such as EVs, hybrid EVs, and this demand is increasing day by day. Now, there is some need to develop these lithium ion battery cells. Actually, this lithium ion cell has a 4-layer structure, a positive electrode which is made with lithium cobalt oxide. It has a current collector which made of thin aluminum foil, which is cathode. And anode is especially carbon, has a current collector of thin copper foil. There is a separator which is fine porous polymer film. And organic solvent with lithium salt is used for electrolyte solution. This is the structure of this lithium ion battery, and the principle is charge discharge principle is like this. Lithium cobalt oxygen is reacted with carbon, and some electrons are getting removed, and this Li 1 minus X cobalt oxygen and C6LX is formed. Now, this cathode material, which is made up from lithium liberating compounds, are typically of 3 types. That is lithium cobalt oxide, lithium manganese oxide, and lithium nickel oxides. But these electrodes are with high rate capability. We need high rate capability, higher charge capacity, and sufficient high voltage, which can improve our energy and power densities of these batteries. So to improve this technology, in present days, these LIVs have working voltage, energy density, and rate capability are mainly of the theoretical capacity and thermodynamics of this cathode material. So our need for develop these promising cathode materials is in a critical condition. So we move to the nanomaterials for LIDs. These are the most promising and provide multiple advantages, such as short path distance from lithium ions and electrons transport, a higher contact area with electrolyte, and better accommodation of the strain which caused by this lithiation and delithiation processes. So, charging to make faster charging speed than those achieved with these conventional bulk materials, we go for the nanomaterials. So there are some disadvantages of these lithium-ion batteries. There is to improve these types of facilities. These batteries are so much expensive. The protection of these batteries required. There is some aging effect, transportation problem, deep discharge, safety concerns, and they are very much sensitive to high temperature. So we move to the grid energy storage systems to supply renewable energy to a large portions. And the facilities of this grid system energy storage is for these capacitors there is high power density, but for the battery we have used there is better high energy densities. So there is only high energy densities is deficiency in this grid system model. So we improve only one system to this supercapacitor model system. So we turn over supercapacitor. Why in a normal capacitor there is energy density is small. So we improve only one this high energy density, high power density, high capacitance, and longer life. A supercapacitor is also called an ultra capacitor, which is an electrochemical capacitor, which have particular applications for hybrid vehicles and as supplementary storage for battery electric vehicles. There is some obstacles to grow this supercapacitor model. They are relatively high cost. The competition with batteries will have established on the market. So we need consumer conservation. Which are the factors to grow the supercapacitor market in India? The new market opportunities like HEVs, high vehicles, smart grid, alternative or renewable energy sources, growing ecology restrictions for competitors, and operation in wide temperature range, good prospects or combined power supply. These are the visible applications of supercapacitors in India. Mahindra E2 and e-rickshaw Rahi from Hero. There is 3 types of supercapacitors we have been already used. That is electric double layered capacitor, hybrid supercapacitors, pseudocapacitors. Only the materials we have used is different. For EDLC, carbon foam, graphene or activated carbon used. In hybrid supercapacitors, asymmetric pseudo, composite compound, and rechargeable battery type, this type of supercapacitor. And for pseudocapacitors, the conducting polymer or metal oxides. We have used metal oxides for these pseudo capacitors systems. So I am going later this graph. So there is different applications of these capacitors. They are used in electronic applications such as cellular electronics or power conditioning, uninterruptible power supplies. They used industrial lasers, medical equipment. They are used in wireless communication systems. They are used in VCRs, CD players, electronic toys, computers, scanners, etc. But there is some disadvantages also. The amount of energy stored per unit weight is considerably lower than an electrochemical battery. The voltage varies with the energy stored. To effectively store and recover energy requires electronic control and switching equipment. It has highest dielectric absorption of all types of capacitors. So here is one materials, nickel oxide thin film we have used for this supercapacitance property. Why we use nickel oxide? Because in other oxide systems, this nickel oxide is environmental friendliness. It has natural abundances. Multiple oxidation states makes it fast redox material. High theoretical specific capacitance. So we have prepared these nickel oxide samples by Schiller technique, successive ionic layer reduction and adduction. And there is, we take three precursors and substrate of glass. So dipped in these three precursors in different time. Here we take 10 seconds. And at last, this nickel oxide film was annealed, prepared, and then annealed the substrate in 350 degrees Celsius in a furnace. So there are 4 samples we have prepared for different dipping cycles. First, for 20 dipping circles, one dipping is in dipping NiNO3 plus NH4OH for 10 seconds, then 1% H2O2 solution 10 seconds, and then distilled water 10 seconds. This is completed one cycle. So these are 20 cycles. For 20 dipping cycles, we get NiO1, for 30 NiO2, for 40 NiO3, and for 50 dipping cycles, we get NiO4. Then we get its XRT, and we get peaks in different positions, which corresponds to 111, 200, 222, 220, 311 planes, which confirms formation of single cubic NiO. And this is the thickness of the film with deposition cycles and grain size, which gives that increasing deposition cycle. The thickness of the film is increasing, but the grain size is decreasing up to 40 deposition cycle, but then it's increasing for certain range. FTIR Fourier transform infrared analysis shows that no significant change of peak position or intensity for the deposited films. This is a surface normalizing. So SEM. This shows that formation of well adherent and porous nanoflakes like structures, and for NiO3 the porosity is maximum. And same image shows the particle size, which is estimated 14.6 nanometer. SAD pattern confirms the presence of 111, 200, 220, and 311 planes, which is cubic nickel oxide for my choice. And is the thin film is showing our capacitance property? Yes. For cyclic voltammetric analysis, we get this, and electrolyte, here we use electrolyte 1 mole of KOH, and it gives the maximum specific capacitance value of 1341 Faraday per gram. We have also done galvanostatic charge discharge analysis, and which gives maximum specific capacitance value 877 Faraday per gram at current density of ampere per gram, which contribution of resistive drop and slow kinetics of radix Bishop Faradic mechanism. And cyclic retentivity and Regan plot gives that capacitance retentivity 90% after 1000 cycles. So it shows high specific energy of 64.4 watt hour kilo per gram and specific power of 2.305 kilowatt kg per gram kilo per kilogram, and good coulombic efficiency is 95.4%. So we get formation of well-adherent porous nanoflake-like structure, maximum specific capacitance from CV analysis, that is 1341 Faraday per gram, and from GCD analysis it is 877 Faraday per gram, capacitance retentivity about 90% after 100 cycles. This is the paper. And there is many research facilities in India for these supercapacitor materials. Synthesis routes are different. We get thin films from sealer, but there is different physical and chemical processes for deposited these thin films. Actually, physical processes are very highly cost effective. So we go to the chemical process, and sealer technique is much easier. And as the chemicals we have used, this is no toxic materials. So there is different research facilities in India for the supercapacitor materials. We have characterized this, and there is different research possibilities for these energy stores laboratories in these particular supercapacitor systems in different areas of India. So up to this, thank you. If there is any question.
Thank you, Dr. Mandal. So I think there are some questions. That was a nice talk, by the way, but I couldn't hear it properly because there were some other pressing needs came due to some feedback from issues. But that's okay. Let me just read over the questions. So I can see right now one from Dr. Somnath Jalal. He's saying, what is charging rate or time in this supercapacitor?
A very small charging rate, but it happens. I think the quality of thin films would be better, so charging rate would be very much very high. As we have only tested why we have produced the supercapacitor in our lab.
Okay, so he also said that's a nice work. And Arijit Mandal has a question. Can we resolve the low energy per unit weight problem by using a substrate containing very much porous surface?
I think porous substance can reduce this problem. So we go for the thin film material. Other material we have not checked.
Okay, so I think this question What is the difference between current generation computer? Now that's for the previous speaker, so just missed it. Okay, so these are the two questions. Thank you so much, Dr. Mandal,
Thank you, Shatpagina.
for the nice presentation. So now we have come to the very end of our webinar. So I will not just make it long, just a formal thing to follow. That is the vote of thanks. I'll just read it out and then we all can go home. So on behalf of our college, the KPC Mahavidyalaya, and the organizing team of this webinar, I would first like to thank all the esteemed speakers of this webinar who graciously agreed to be a part of it and give enriching and insightful oral presentations before us. Just to go a little bit more detail, we thank our first speaker, Dr. Soham Ghosh, for wonderfully describing density functional theory before us and also analyzing surfaces of oxide systems like SR2, RuO4, and SRTiO3 with that tool. Thanks to the second speaker, Dr. Arijit Saha, who took over the session from there and so nicely explained the intricate topic of topology in condensed matter systems and discussed on many avenues of study that deal with such concepts nowadays. Thereafter, we had two short presentations with Mr. Anupam Saha and Dr. Pampa Pal Goswami. Thanks to the speakers for whom we got to see the features of quantum oscillations in topological nodal line semimetals and to know about preparation and characterization of magnetic nanoparticles of industrial and medical applications. Then as we move on to our today's session, we were enthralled to witness the great talk by Dr. Ananda Dasgupta, who discussed quantum key distribution, Schrodinger's cat, and then if I say it a little light manner, he made us understand how this would have helped Mr. Sherlock Holmes in accomplishing his duties. So special thanks to Dr. Dasgupta for that. Thereafter, we had the opportunity to listen to our contributory speaker, Dr. Somnath Jalal. Thanks to him for very delicately explaining the connection between a 2D classicalizing model and a 1D quantumizing model. Thanks to him also for bringing some flavors of classical thing among the dominance of quantumness in this webinar. Then our second contributory speaker, Dr. Amit De, took over the session and enlightened us on stimulated Raman adiabatic passage via cavity QED based platforms. We thank him for presenting an exciting talk before us. Then we again got to listen to two short presentations. Thanks to our student, Mr. Rajdeep Banerjee, for his nice compilation of current facts and researches on quantum tunneling and presenting that before us. Then we also thank our colleague, Dr. Shampa Mondol, who later on discussed on the important topic of energy storage and how to incorporate that in various fields. We thank all our speakers for their exciting and thought-provoking presentations before us and to make this webinar a success. At the same time, we are very thankful to all the participants for their patience in listening to the long talks, as well as their active participation and exciting queries to the speakers. We acknowledge that they are the integral part of any seminar or webinar, without whom no event can even proceed. So thank you very much to you all. Now I'll look back to my college, and my first thanks will go to our principal, Dr. Paramartha Ghosh. Without his encouragement, it will not be possible to conduct this event. We also thank him for starting the webinar with his introductory note. My thanks also to IQAC of our college and the IQAC coordinator, Dr. Ashish Kaur, as IQAC collaborated with physics department to organize this event. Lastly, I should thank the organizing team. Thanks to our head of the department, Mr. Rajiv Kumar Mondol, my colleagues, Dr. Shampa Mondol, Mr. Surojit Gwin, and Mr. Ashish Mondol, for constant planning and discussion on how to make this event a success. And my special thanks to Dr. Saurav Haldar, Assistant Professor of Mathematics of our college. Dr. Haldar single-handedly hosted 2 days Google Meet sessions of the webinar and arranged for the YouTube streaming. So many thanks to him. So this is the end of the event. Thank you all the participants. We spent some quality time with you all in these 2 days webinar sessions. Before you leave, please don't forget to fill up the feedback form. Sorry for the fiasco that you had to suffer, you had to face for that. Make sure there is no typo there, as that would then go directly to your certificate. The certificate will be emailed to you within 2 weeks from now. So thank you very much. So that is all. So here we'll just formally close today's session. Thanks a lot.